Guys, can you all hear me? Am I audible, visible to you? Just say it once in the chats. Yeah? Perfect, guys. So, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So, there was basically a technical glitch. I was live on JE channel, but I was supposed to be live on this particular channel, right? So, can you all hear me now? Am I like perfectly audible, visible to you? Like all the things are absolutely clear, right? Just give me some green signal from the chats. Give me some green signal from the chats, people. Quickly, everyone in the chats. Everyone. So basically, today it's going to be the third session of the electrochemistry chapter. And my dear students, today we are going to discuss the most important topic of the chapter. I'll say the most important topic of the chapter. And the name of the topic is going to be Nernst equation. You must have heard about it, right? Guys, it is, again, I'm telling you, it is the most important topic of the chapter because majority of the times, whenever question is asked from the chapter electrochemistry, majority of the times the question is asked from the Nernst equation itself. And in this particular session, we are going to start the Nernst equation and we are going to complete the Nernst equation at the same time. We'll first of all see what this Nernst equation is, and after that, we'll see all its applications. Okay? So are you all ready for it? Are you all ready for it? Quickly in the chats. Quickly in the chats. Are you all ready for it? Let me know quickly in the chats. Everyone. Yes, exactly. We are meeting after long, right? We are actually meeting after 10 days, I believe. Right? You know, I was basically busy with a lot of stuff. I kept you updated about everything in the Telegram group. Okay? So from now onwards, we are going to have the regular sessions on this particular channel as well. Okay? Perfect, guys. So let's get going then. Let's get started. One thing which I would want to share with you, whatever I'll be mentioning on the screen, whatever I'll be writing on the screen, I would want you guys to take a note of every single thing. Because every single thing is going to be really very important when it comes to the Nernst equation. Okay? Perfect. So let's get going then. Let's get started. My dear students, if you remember in electrochemistry, what all topics we have discussed till now. First of all, we started with something called as galvanic cell, if you remember, right? We discussed how galvanic cell exactly works, how Daniell cell exactly works. Then I told you how do we represent a galvanic cell. That was the second topic. The third topic was how to write the net cell reactions from a given cell. That was the third topic. Fourth topic was your electrode potential and its significance, right? Fifth topic was how do you calculate the standard EMF of the cell, E0 cell, which used to be E0 of cathode minus E0 of anode. I hope all those things you exactly remember, which we already discussed in the chapter electrochemistry, right? Okay. Now we will try to understand what exactly I'm going to say. Now we are going to discuss something called as Nernst equation. So let's exactly get to know what this Nernst equation is all about. Okay. Let's have a look, people. Let's have a look. Tell me in the chats whether the video clarity is proper. Is the video clarity proper? Say yes or no in the chats. Say yes or no in the chats quickly. Quickly, everyone. Is the video clarity all okay? Let me know quickly because somebody wrote video clarity should be increased. I think you should increase your video clarity in the settings. Yeah? Because on my side, I believe everything is okay. Yes, Sumanti, you can enroll still. You can still enroll into the batch. No issues. The link is there in the description. Okay. So let's try to get this Nernst equation. My dear students, what this Nernst equation is, I'll be first of all deriving it. If you remember, there was one equation which you all must be knowing from the chapter Thermodynamics. And the equation was delta G is equal to delta G naught plus RT ln of QC. I hope you remember this particular equation, which we have discussed in thermodynamics. If you do not remember it, do remember it from now onwards. Delta G, it is always equal to delta G naught plus RT ln of Q, where Q is the reaction quotient. You know it. Now, my dear students, if I particularly talk about the galvanic cell, for a galvanic cell, in case of the galvanic cell, can you let me know what delta G exactly is all about? We have discussed this in the last session. Delta G for the galvanic cell is equal to minus NF cell, right? And delta G naught is equal to minus NF naught cell. These were the things which we have already discussed, right? Now, people, understand. If I put these two parameters into the main equation, what do I get? Instead of delta G, I'll be writing minus NF cell is equal to, instead of delta G naught, I'll be writing minus NF naught cell. Minus NF naught cell. It's going to be plus, this is RT, this is ln of QC. Okay? Now, first of all, if I divide this equation throughout by what? If I divide this equation throughout by NF, I'm dividing this particular term by NF. I'm dividing this particular term by NF. And at the same time, I'll be dividing this particular term with NF as well, right? So NF cancelled. So I'll be getting, okay, you can do one more thing. You can multiply throughout with the minus sign. When you multiply throughout with the minus sign, NF cancelled, minus becomes plus. So you are getting one equation here, which is E cell is equal to E naught cell minus E naught cell minus, this is RT divided by NF, and it's going to be ln of QC. This particular equation which is made over here. My dear students, this particular equation which is formed over here, which is made over here, this particular equation is something which you call as Nernst equation. This is something which you call as Nernst equation. Okay? So E cell is equal to E naught cell minus RT divided by NF ln of QC. Now, let me further simplify it a bit. Have a look. So you can write something like this. E cell you are going to write as such. Is equal to E naught cell you are going to write as such minus. This is ln of QC. So convert it into log. So it has to be 2.303 RT divided by NF, and now it's going to be log of QC, right? This is one more form of the Nernst equation, which is something I call as the logarithmic form. This is something which I call as the logarithmic form of the Nernst equation. Now, my dear students, try to understand the parameters which are there in the equation. Once you get to know the parameters, then I can show you its application form. Where do we exactly need this particular equation? Before that, what is this E cell over here? E cell is something which you call as EMF of the cell. E cell is something which you call as EMF of the cell, but under which conditions? Under non-standard conditions. Under non-standard conditions. I hope you all remember what are standard conditions and what are non-standard conditions. In case of standard conditions, concentration is taken as 1 molar, pressure is taken as 1 bar, right? And temperature is generally kept constant, right? Temperature is kept constant, generally 25 degrees centigrade. Perfect. So E cell is something which you call as the EMF of the cell under non-standard conditions. I hope you remember what EMF is. What is the EMF? EMF is the maximum potential difference between the electrodes in the galvanic cell when the cell is not in use. Discuss that in detail, right? Already we have discussed that in detail. EMF is basically the maximum potential difference between the electrodes when the cell is not in use, when no current is drawn from the cell, right? And EMF is measured with the help of potentiometer. I hope you remember that. Now, people, what is E naught cell? What is E naught cell? E naught cell is something which you call as standard EMF of the cell. This is something which you call as standard EMF of the cell. And I hope you guys remember, how do we calculate E naught cell? It is calculated like this. E naught cathode minus E naught anode. What is E naught cathode? This is something which you call as standard reduction potential of cathode. And this particular term is your standard reduction potential of anode. This is how you calculate E0 cell as well. Okay. I hope you remember what this N exactly is. If I ask you what is this N over here, N represents number of moles of electrons exchanged in the net cell reaction. Number of moles of electrons exchanged in the net cell reaction. And I have taught you in detail how do we get the N value, right? What is this F over here? F is the Faraday's constant. F is the Faraday's constant whose value is 96500 coulombs, right? And what is this QC over here? QC is something which you call as reaction quotient. QC is something which you call as reaction quotient. And if you remember already, I have taught you how to get the reaction quotient of a particular reaction. What is this T over here? T is the temperature at which the cell is working. And R, it's a constant whose value you already know, that's 8.314 joules per Kelvin per mole. Correct? Now, my dear students, try to understand what exactly I'm going to say. Something important I'm going to discuss with you. See, we got the equation. The equation is something like this. E cell is equal to E0 cell minus 2.303 RT divided by NF, and then we are going to write log of QC. This is something which you call as the Nernst equation. Now, my dear students, in the questions, I'm not going to use this equation always. In the questions, I'm going to simplify this equation a bit, right? And after simplifying, we'll be getting one comparatively simple equation, and that simple equation we'll be using in the questions. And how do we get that equation? See, guys, if I keep the temperature as 25 degrees centigrade, which means 298 Kelvin, right? If I take the Faraday's constant as 96500 coulombs, right? If I take the value of R as 8.314 joules per Kelvin per mole. If I put all these parameters into the equation, what do I get finally? I'll be getting something like this. E cell is equal. It is going to be E0 cell minus 0.0591 divided by N, and then it's going to be log of QC. This is the equation which I'll be using in majority of the questions in case of the Nernst, right? Okay. E cell is equal to E0 cell minus 0.0591 divided by N, then it's going to be log of QC. My dear students, do you remember how do we calculate E0 cell? I have discussed this with you. E0 cell is equal to E0 cathode minus E0 anode. Do you remember how do we get the N value? Number of moles of electrons exchanged in the net cell reaction. For that purpose, we write reaction at anode, then we write reaction at cathode, then we try to balance the electrons, then we try to add the reactions, and once we add the reactions, there will be the electrons which gets cancelled out, right? That gives you the N value. I hope you remember. And I hope you remember how to get the QC value as well. This is something which we have discussed too, right? So basically, whatever parameters we need in the Nernst equation, all those parameters we have already discussed. Now, what we need to do is, we need to put those parameters, we need to put the value of those parameters into this equation and get the value of E cell. Okay? So number one, this equation is what you call as Nernst equation. Now the point is, where all do we use this equation? What about its application? My dear students, let me exactly tell you where all do we use this particular Nernst equation. Okay? So first of all, Nernst equation is used in half cells. Half cells means electrode, right? You know, a complete cell, a complete galvanic cell, that's made up of two electrodes, right? Or you can say a complete galvanic cell, it's made up of two half cells. Half cell is equal to electrode, right? Half cell is equal to electrode. You can use this particular equation for the half cells. Why? My dear students, in order to calculate the oxidation potential of any electrode under non-standard conditions, or in order to calculate the reduction potential of any electrode under non-standard conditions, I'll be using this particular equation. In order to calculate the oxidation potential of the half cell, the oxidation potential of the electrode, or the reduction potential of the electrode under non-standard conditions, at that point of time, I'll be using this particular equation. And how exactly I'm going to write this? Imagine that I need to calculate reduction potential of some electrode under non-standard conditions. How do I write this equation? You'll be writing this equation in a different format. You'll write ERED, which represents the reduction potential of the half cell. is equal to E naught RED. E naught RED means standard reduction potential of the same electrode, right? Minus 0.0591 divided by N. And then it's going to be log of what? Log of QC. So this particular equation is used to calculate the reduction potential of the half cell under non-standard conditions. Okay? My dear students, in the similar way, whenever you need to calculate the oxidation potential of the half cell under non-standard conditions, again, you'll be using this particular equation. And how do you write this equation at that time? You'll write EOX. Instead of E cell, you'll be writing EOX, which represents oxidation potential of the half cell under non-standard conditions, is equal to E naught OX. E naught OX represents standard oxidation potential of the half cell minus 0.0591 divided by N. Then it's going to be log of QC. Where do we use this particular equation? My dear students, whenever you'll be given with the electrode, whenever you'll be given with a half cell, and you will be supposed to calculate the oxidation potential or reduction potential of that half cell under non-standard conditions. You'll be using this Nernst equation in these two forms, right? If you are supposed to calculate the reduction potential of the half cell, use this equation. If you are supposed to calculate oxidation potential of the half cell, use this particular equation. That's all, right? Okay. Is this point clear to everyone? Now, one by one, in detail, we are going to discuss how this Nernst equation exactly is used. Okay. So first of all, I'll show you how Nernst equation is used in case of electrodes, or electrode is something which you call as half cell. Okay. Try to understand what exactly I'm going to say. Imagine that I've taken a container. Let's say this is the container. And my dear students, in this particular container, imagine that there is an electrolyte. Is it fine now? Is it fine now? Quickly, let me know in the chats. It should be okay now, I believe. Yeah? Guys, just refresh once. Just refresh once. Okay, now it's fine. All right, perfect. All right, guys, try to understand what exactly I'm going to say. Imagine that this is the container, and in this container, you have kept the ions. Which ions? Mn positive ions, right? And in this particular container, you have dropped a rod. There is a rod which is made up of element M. There is a rod which is made up of element M. And this particular rod is introduced into a solution containing its own ions, right? I've taken a rod, right? And this rod is introduced into a solution which contains its own ions. Perfect. So I'll be calling this whole setup as electrode. This whole setup should be called as electrode. Now, my dear students, this particular electrode, which I've taken over here, it can work like cathode, it can work like anode as well. You know it already. Imagine that this particular electrode is working like cathode. Imagine that the electrode is behaving like the cathode. Okay. Now tell me one thing. When this particular electrode behaves like the cathode, what is going to happen? Oxidation or reduction? Reduction will happen. Because at cathode, always reduction takes place. A reduction means gain of electrons. So what exactly is going to happen? My dear students, these Mn positive ions, which are there in the solution, they are going to collide with the rod. They are going to take N electrons from the rod. So the reaction has to be something like this. Mn positives, which were there in the solution, they are going to collide with the rod. They are going to take N electrons out from the rod, and it will get converted into M solid. This has to be the reaction when this particular electrode behaves like the cathode, right? Now tell me one thing. In this particular reaction, if I ask you how many moles of electrons are exchanged, in this particular reaction, I must say N moles of electrons are exchanged. Now, dear students, if I ask you to write the reaction quotient for this particular reaction, you'll start with the product. which is in solid form, its active mass is unity divided by, it's going to be concentration of Mn positive raised by its stoichiometric coefficient. That's 1. Okay, perfect. Now, my dear students, I want you guys to calculate the reduction potential of this particular electrode. Imagine for example, the concentration of Mn positive is anything, 3 molar, 4 molar, 5 molar, right? Imagine the concentration of Mn positive in the container is anything, 3 molar, 5 molar, 6 molar, anything, right? So basically, is this electrode present under standard conditions or non-standard conditions? I'm not keeping the concentration of electrolyte here as 1 molar. I'm keeping it different. So this particular electrode is present under non-standard conditions. Now, under non-standard conditions, I want you to calculate the reduction potential of this half cell, the reduction potential of this electrode. And the reduction potential of the electrode under non-standard conditions is calculated with the help of Nernst equation. It is calculated with the help of Nernst equation, right? My dear students, basically what am I asking you to calculate? Try to understand one thing. If you remember, we have discussed this in detail. See, basically initially in the container, there were equal number of cations and anions. Initially in the container, there were equal number of cations and anions. Now, the cation in the container is colliding with the rod. It is taking electrons from the rod, getting converted into what? Getting converted into M solid. And that M solid will be deposited on the rod. Tell me, is the amount of cations in the container increasing or decreasing? Is the amount of cations in the container increasing or decreasing? I'll say amount of cations in the container is decreasing because Mn positives, they are undergoing reduction, getting converted into M solid, and that M solid is deposited on the rod basically, right? So the amount of cations in the container are decreasing. If the cations are decreasing, anions in the container are remaining the same, but cations are decreasing. So this solution will effectively get which charge? This solution will get effectively negative charge. And my dear students, these Mn positive ions, they have collided with the rod. They have taken electrons from the rod. If electrons are taken from the rod, then the rod gets which charge? Positive charge, right? So tell me one thing. The rod got positive charge. Solution got negative charge. Can I say between the rod and the solution, a potential difference is getting created? A potential difference is getting created between the rod and the solution. And that potential difference is what you call as electrode potential basically, right? That's what you call as electrode potential. Imagine the conditions are not standard. So I'll be calling this electrode potential under non-standard conditions, right? Perfect. So what I simply did, leave all this aside. We have discussed this in detail. I just need one thing here. I told you that I've got an electrode and I want to calculate its reduction potential under non-standard conditions. Okay. So till here, I'm done. Now, in order to calculate reduction potential under non-standard conditions, I'll be using the Nernst equation. Nernst equation says that ERED, reduction potential of the same electrode under non-standard conditions, is equal to E naught RED, which is standard reduction potential of the same electrode, minus 0.0591 divided by N, and it's going to be log of QC. What is QC? QC is 1 divided by concentration of Mn positive, right? This is how you guys are going to calculate. The reduction potential of the half cell under non-standard conditions. This particular term represents what? It represents the reduction potential of the half cell. Under which conditions? Under non-standard conditions. This particular term represents standard reduction potential of this electrode, standard reduction potential of the half cell, right? And N already you know, it represents moles of electrons exchanged. Now tell me one thing. Guys. One thing I want you guys to learn from here. See, imagine that I'm increasing the concentration of electrolyte in the container. If I increase the concentration of electrolyte in the container, tell me what will happen to the concentration of Mn positives. These Mn positives, how they are coming into the container when the electrolyte is undergoing dissociation. If I'm increasing the amount of electrolyte in the container, can I say the concentration of Mn positives in the container will increase? Absolutely. the concentration of Mn positives in the container will increase. Now use simple mathematics here. You are increasing the concentration of Mn positives in the container by adding more electrolyte. You are increasing the electrolyte in the container. So you are increasing the concentration of Mn positive. That means you are increasing the denominator here. If you increase the denominator, what will happen to this particular value? This value will decrease. You are increasing the denominator. So this whole value is decreasing. If this value is decreasing, I would say this whole value will be decreasing. If this whole value is decreasing, what will happen to the difference of these two terms? If this value is decreasing, I must say the difference between these two terms, it will increase. If the difference between these two terms increases, that actually means your reduction potential is increasing. That actually means reduction potential of the half cell that is increasing. So from here, we can generalize one very important statement. And what is the statement all about? Statement is very simple. On increasing the concentration of electrolyte in the container, the reduction potential of the half cell that increases. Okay, what is meant by this? Let's try to understand this a bit more in detail. See guys, imagine that this is the zinc electrode. This is the zinc rod, and you have introduced the zinc rod into zinc sulfate, right? You have got one more zinc electrode here. This is your zinc rod, which is introduced into zinc sulfate, right? Electrodes are same. Both are zinc electrodes, right? Now tell me one thing. Imagine the concentration of zinc sulfate here is 2 molar and the concentration of zinc sulfate here I have kept as 5 molar. Will the reduction potential of both the electrodes be same or different? Since the concentration of electrolyte is kept different, that electrode in which the concentration of electrolyte is more, will have more reduction potential. Is it simple? So I would say this particular electrode will have more reduction potential than this particular electrode. Yes? Agreed? So do remember, this is one very important thing. With the increase in the concentration of electrolyte, a reduction potential of the electrode, it automatically increases. Okay? Now people, so this is how you calculate the reduction potential of the half cell. Okay? Now people, now the point is, how do we calculate oxidation potential of the half cell? How do we calculate the oxidation potential of the half cell? Tell me one thing. Imagine I'm taking the same electrode which I took few minutes back. Let's say this is your container, and in this container what do we have? We have got Mn positive ions, and here you have introduced a metal rod. So this is an electrode. Now my dear students, I want to calculate the oxidation potential of this half cell under non-standard conditions. In order to calculate oxidation potential, I'll make sure this electrode behaves like the anode. Why? Because at anode only oxidation takes place. So I'll make sure that this electrode behaves like the anode. When this electrode behaves like the anode, what will happen? Oxidation, right? So this rod is basically made up of metal atoms, and those metal atoms will undergo oxidation. They'll lose electrons, and those metal atoms, they'll get converted into Mn positives, and Mn positives will enter into the solution, and you'll be getting some N electrons here. Perfect. This is the reaction which will happen when this particular electrode behaves like the anode. Right? Now try to understand. This represents number of moles of electrons exchanged, right? Now, I'm asking you to get the QC value. Start with the product. It's going to be concentration of Mn positive raised by stoichiometric coefficient, that's 1. This is in solid state, it's hectomasses unity. Now, my dear students, what exactly am I going to do? I made sure that electrode behaves like the anode. At anode, oxidation takes place. So basically, I'm asking you to calculate the oxidation potential of this particular half cell. Oxidation potential of this electrode. As per Nernst equation, it has to be equal to E naught OX, standard oxidation potential of the same electrode, minus 0.0591 divided by N, and then it's going to be log of QC. And QC value is nothing, that's concentration of Mn positive. Clear? So with the help of this particular equation, I will be calculating the oxidation potential of this particular electrode under non-standard condition. So this is oxidation potential of what? Of the half cell under what? Under non-standard conditions. under non-standard conditions. What is this E naught OX? This is your standard oxidation potential of the same half cell. Okay. Now try to understand one thing here. My dear students, if I increase the concentration of electrolyte in the container, if I increase the concentration of electrolyte in the container, what will happen due to that? Due to that, I would say the concentration of Mn positives will increase. The concentration of Mn positives will increase. Now, if the concentration of Mn positive is increasing, if this term is increasing, that means this term is increasing. If this term is increasing, that means this term is increasing. If this particular term is increasing, that means the difference between the two will decrease. If the difference between the two is decreasing, what does that mean? That means indirectly oxidation potential is decreasing. So indirectly oxidation potential is decreasing. So do remember this particular scenario as well. Upon increasing the concentration of electrolyte in the container, the oxidation potential of the half cell, the oxidation potential of the electrode, it decreases. Is this point clear to everyone? Say yes or no in the chats quickly with the thumbs ups. Is this point clear to everyone? So with the increase in the concentration of electrolyte, reduction potential of the electrode increases. And it's evident, if reduction potential of the electrode increases, automatically oxidation potential of the same electrode, that will decrease, right? Let me know once in the chats quickly, everyone. Everyone, people, everyone. Yeah, it's clear? Wonderful. All right. So I hope you got to know how do we calculate the oxidation potential and reduction potential of the half cells of the electrodes under non-standard conditions, right? And my dear students, after some time, I'll be giving a lot of questions on the same equations so that you'll understand it in a better way, right? But right now, this much is enough. Okay, after some time, I'll give you the questions. Before solving the equations, there are a few more things which I want to share with you. What are those things? Nernst equation for hydrogen electrode. How do you exactly write the Nernst equation for hydrogen electrode? Try to understand. I hope you guys remember how we exactly make the hydrogen electrode. I hope you remember. This is the container. In this particular container, what are we keeping? In this particular container, we are keeping H positives, right? This concentration of H positive can be anything. I'm keeping H positives in the container. And my dear students, over here, this is the inverted U-type tube, which I'm keeping over here, right? And if you remember, there's a platinum wire, which is coated with platinum black. I hope you remember this as well. This is the platinum wire, which is coated with platinum black, right? And over here on this side, I'm introducing H2 gas. What is going to happen? This H2 gas will adsorb on the surface of platinum. And I'll make sure this H2 gas, which I'm introducing, it gets adsorbed on the whole surface of platinum, right? I'll introduce H2 gas, still the whole surface of platinum is covered by H2 gas. Can I say, after continuously the introduction of H2 gas, can I say there'll be a scenario when this platinum wire is completely covered with H2 gas, right? So it looks like a hydrogen rod to me. It does not look like a platinum rod now. It looks like a hydrogen rod because its entire surface is covered with hydrogen gas. Now put this hydrogen rod and introduce in H positives, right? So hydrogen rod introduced into its own ions. So this whole setup I'll be calling as electrode. Now which electrode this is? This is the hydrogen electrode. This is the hydrogen electrode, right? This is the hydrogen electrode. Now tell me one thing. Imagine the pressure at which I'm introducing H2 gas. Imagine that is, for example, 1 bar. The pressure at which I'm introducing hydrogen gas. Imagine that's 1 bar, right? Now guys, this particular hydrogen electrode which we have, this hydrogen electrode, it can behave like anode or it can behave like cathode, right? Imagine that this particular hydrogen electrode is behaving like the anode. When the hydrogen electrode behaves like the anode, what's going to happen? Oxidation is going to happen. The surface is covered with H2 gas, right? So H2 gas on the surface, it will undergo oxidation. And if you remember, when H2 undergoes oxidation, it gets converted into 2 times H positive aqueous, and with that you'll be getting 2 electrons. This is something which is also discussed when I taught you the hydrogen electrode formation long back. So when this particular hydrogen electrode, when it behaves like the anode, this is the reaction which is going to happen, which I call as the oxidation reaction. Now, my dear students, in this particular reaction, if I ask you how many moles of electrons are exchanged, I would say 2 moles of electrons are exchanged. 2 moles of electrons are exchanged in this reaction. Okay. Tell me what is the value of QC? QC value. Start with the product. It is concentration of H positive raised power 2 divided by, this is partial pressure of H2, and partial pressure of H2 I have kept as 1 bar. So leave that aside. Okay. So this is your QC value. Now, my dear students, since this electrode, this hydrogen electrode is behaving like the anode, and at anode oxidation takes place, right? Imagine I want to calculate the oxidation potential of this hydrogen electrode under non-standard conditions. So I'll be using the Nernst equation. I'll say EOX, oxidation potential of this hydrogen electrode, is equal to E naught OX, standard oxidation potential of the same hydrogen electrode, minus 0.0591 divided by N. Then it's going to be log of QC. This is how you are going to write Nernst equation. To calculate what? To calculate oxidation potential of this particular hydrogen electrode under non-standard conditions. Now, my dear students, you guys are going to tell me one thing. You guys are going to tell me one thing. What is E naught OX? That is standard oxidation potential. If you remember, SOP, SRP of hydrogen electrode as per convention is taken as 0. Do you remember that? Right? SOP as well. This is SOP of hydrogen electrode. And you know SOP as well as SRP of hydrogen electrode, that's taken as 0. So this particular term is already 0. Now minus 0.0591 divided by what? Divided by N. Log of QC. So it's going to be log of QC is nothing. That's concentration of H positive ka square. Correct? Now guys, tell me one thing. Log of M raised power N. Log of M raised power N is N log M. So I can write it like this. EOX is equal to minus 0.0591 divided by N value is 2. So this is 2 log of H positive. Log of H positive concentration. As simple as that. Right? As simple as that. Now after this, what am I going to do? Try to understand. After this, what exactly am I going to do? Try to understand. I'll write EOX is equal to. EOX is equal to. This 2 and 2 gets cancelled out. I'll just write 0.0591. And this minus I'll take inside. So it's minus log of H positive. Minus log of H positive is something which you call as minus log of H positive, something which you call as pH. So my dear students, this is one general result which I got to calculate the oxidation potential of the hydrogen electrode in which the partial pressure of H2 is 1 bar. Right? In which the partial pressure of H2 is 1 bar. If the partial pressure of H2 is changed, if it's not 1 bar, then you cannot use this relation. You cannot use this relation. This relation is only valid when the partial pressure of H2 is 1 bar. Now guys, tell me one thing. Can I say oxidation potential of the hydrogen electrode depends on the pH of this solution? It depends on the pH of this particular solution, right? Okay, so can I say on increasing the pH of the solution, the oxidation potential of the hydrogen electrode, does it increase or decrease? It will absolutely increase, right? Oxidation potential is directly proportional to pH. If you increase the pH of the solution, I would say its oxidation potential will automatically increase. Right, people? Is it clear to everyone? Quickly in the chats. Quickly in the chats. Let me know quickly in the chats if all the things are absolutely clear. Right? Okay. So what I was telling you, this is just a general equation by means of which you can calculate the oxidation potential of the hydrogen electrode under non-standard conditions. Now guys, tell me one thing. Can't the same hydrogen electrode behave like the cathode? What do you think? Can't the same hydrogen electrode behave like the cathode? Absolutely. The same hydrogen electrode, it can behave like the cathode as well. Yeah? The same hydrogen electrode, it can behave like cathode as well. And tell me just one thing. When the same hydrogen electrode behaves like the cathode, when the same hydrogen electrode behaves like the cathode, what will happen? A reduction will happen. Reduction will happen. Just reverse this reaction. Just reverse this reaction. So the reaction now is going to be 2 times H positive aqueous plus 2 electrons. It gives what? It gives H2 gas. So this is the reaction when the hydrogen electrode behaves like the cathode. Now guys, how many moles of electrons are exchanged? 2 moles of electrons are exchanged in this particular reaction. Write the expression for QC. QC is going to be, start with the product. It is in gaseous form. So partial pressure of H2, I'm going to take as 1 bar divided by concentration of what? Concentration of H positive raised power 2. And it has to be concentration of H positive raised power minus 2. Simple. Now, I made sure that hydrogen electrode behaves like the cathode. At cathode, reduction takes place. So indirectly, what am I trying to calculate? I'm trying to calculate the reduction potential of the same hydrogen electrode under non-standard conditions. And I'll be using the Nernst equation. Reduction potential of the hydrogen electrode is equal to standard reduction potential of the hydrogen electrode minus 0.0591 divided by N. And it's going to be log of QC. Right? Now, my dear students, in case of hydrogen electrode, this particular term is going to be 0. This is SRP of hydrogen, 0. So it's going to be ERED is equal to minus 0.0591 divided by N value is just 2 and log of QC. QC is concentration of H positive raised power minus 2. Perfect. Now, log of M raised power N. Log of M raised power N, which has to be N log M, right? So I would say ERED is equal to minus 0.0591 divided by 2. Log of M raised power N is N log M. So minus 2 comes to the front. Then it's going to be log of H positive here. Perfect. Simple maths I'm using, nothing else. So 2 and 2 got cancelled out. When 2 and 2 gets cancelled out, what I'll be left with? What I'll be left with? See guys, try to understand. I'll be writing the reduction potential of the hydrogen electrode is equal to minus 0.0591. Oh, this is minus log of H positive, and minus log of H positive is something which you call as pH. Minus log of H positive is something which you call as pH. So I got one more important result over here. The reduction potential of hydrogen electrode, does it depend on pH? Yes, it does depend upon the pH. And you got to know, on increasing the pH of the solution, reduction potential of the hydrogen electrode, it will decrease because the sign here is minus. Right? Perfect. And just try to understand one thing. Look at this equation. ERED is equal to minus 0.0591 multiplied by pH. And look at this equation. AOX is plus 0.0591 into pH. It is evident only. This is something which we already knew. This is something which I've already told you. EOX of an electrode is equal to minus times its ERED. Right? That's something which was already discussed, which was already understood. I hope all these things are clear. I hope all these things are clear to you. Is that people? Right? So this is one more important result. You need to remember this. So when you increase the pH, of this particular solution, oxidation potential of hydrogen electrode will increase and reduction potential of the same electrode, it will decrease. Right? Perfect. Perfect, guys. So I hope you got to know how exactly we are going to use Nernst equation for half cell. Okay? So now, my dear students, let's try to solve few basic questions so that you can understand all these things properly. Look at the first question. From this particular question, you'll exactly get the idea of how we use Nernst equation for the half cells. All the types of questions which can be asked from Nernst equation, I'll be solving all those types of questions here only, right? Afnan, that was a nice one, yeah? Okay, look at this particular question, guys. Try to understand. The question is, we are given with an electrode. Look at the electrode carefully. You have taken an iron rod, and this particular iron rod is introduced in a solution containing FeSO4, right? Simple. So basically you have taken an iron rod. Let me just make it clear to you. Imagine this is the container, and in this particular container, what have we kept? We have kept FeSO4. Now this FeSO4 would have got dissociated as Fe di positive plus SO4 di negative. Now in the same container, you have introduced an iron rod. This is the iron rod which is introduced into a solution containing its own ions. I'll be calling this whole setup. As electrode. So this is an iron electrode, right? And my dear students, what exactly I'm going to do? Look at the question. The question is asking, calculate the oxidation potential of this half cell when the concentration of FeSO4 is kept 0.1 molar. The question says, when the concentration of electrolyte in the container is 0.1 molar, at that point of time, what will be the oxidation potential of this half cell? Yeah? Now have a look. Have a look, people. First of all, initially, as per the question, the concentration of FeSO4 I have kept 0.1 molar. So this has to be 0. This has to be 0. Now imagine that this FeSO4, it gets 100% dissociated into its ions. And when this FeSO4 gets 100% dissociated into its ions, I'll be left with nothing. Now people, 1 mole gives 1 mole, 0.1 molar gives 0.1 molar. This has to be also 0.1 molar. If I ask you, what is the concentration of Fe di positive in the solution? You will say the concentration of Fe di positive in the solution is 0.1 molar. Now you must be thinking, why did I calculate the concentration of Fe di positive? My dear students, I need that concentration of Fe di positive to write QC. Have a look. See, as per the question, what do I need to calculate? I need to calculate oxidation potential of this half cell when the concentration of FeSO4 is 0.1 molar. To calculate the oxidation potential, I'll make sure that the electrode behaves like the anode, because at anode only oxidation takes place, right? At anode only oxidation takes place. Now have a look. What has to be the reaction? At anode, oxidation. Oxidation means loss of electrons. See, this is iron with oxidation state 0. This is iron with oxidation state +2. So iron is changing its oxidation state from 0 to +2. Increase in the oxidation state. Oxidation, loss of electrons. So basically the reaction has to be Fe solid is getting converted into what? Fe solid has to get converted into Fe di positive aqueous, and with this you will be writing 2 electrons. So this is the reaction which will take place when this particular electrode will behave like the anode. Now if I ask you, how many moles of electrons are exchanged in this reaction? I'll say 2 moles of electrons are exchanged. Okay? 2 moles of electrons are exchanged. Tell me, what about QC value? What about QC value? Start with the product. Its concentration of Fe di positive raised power 1 divided by, this is solid, its active mass is unity. Now do you understand why did I calculate the concentration of Fe di positive? Because I needed it here. So the concentration of Fe di positive in the solution is nothing, that is 0.1. Perfect. So QC value is 0.1, right? N value is 2. Now what do I need to calculate? I need to calculate the oxidation potential. So use the Nernst equation. Oxidation potential of the half cell is equal to E naught OX, standard oxidation potential of the half cell, minus 0.0591 divided by N. Then it's going to be log of QC. Perfect. So this is something which I need to calculate. EOX is equal to E naught OX. Look at this particular value. Is this SOP or SRP? See, this is +2 to 0. +2 to 0 means decrease in the oxidation state. Decrease in the oxidation state means the reduction. So this is SRP. But do I need SRP or SOP? We need SOP. So this particular term is SOP, right? This is SRP. So just reverse its sign. So it's plus 0.44. Plus 0.044 minus 0.0591 divided by N value. N value as per the question is 2. Then it's going to be log of QC. QC value, we have already calculated that 0.1, which means 10 raised power minus 1. Now it's a matter of calculation only. This is 0.0591 divided by 2, and it's log of m raised power n, n log m. So minus 1 comes to the front, log 10 is 1. So just solve this value and get the answer in volts. That's going to be the oxidation potential of this particular half cell, right? Okay. Whatever you get from here, that's going to give you the oxidation potential of the half cell, which you were supposed to calculate. Imagine that you were supposed to calculate the reduction potential of the same half cell. Since you calculated the oxidation potential, just reverse its sign. You'll be getting the reduction potential of the same half cell as well, when the concentration of FeSO4 is taken as 0.1 molar. Is this clear? Let me know once in the chats, people, quickly. Quickly. Priya is saying it's 0.046, right? Okay. It is 0.0, I think 47, right? This is the oxidation potential of this particular half cell. So its reduction potential will be minus times this. Okay? This sort of a question, I believe you can solve easily from now onwards. Look at the next question. Look at this particular question. Calculate the oxidation potential of this particular half cell. Your half cell is H2 gas. This side you have got HCl. So HCl in the container would have dissociated as H positive plus Cl negative. So I'm making it in the simpler format like this. Imagine that in this container you have kept HCl, and this HCl would have got dissociated as H positive plus Cl negative. The concentration of HCl which you have taken, that is 0.1 molar. So initially this will be 0, this will be 0. Now finally this is 0, this will be 0.1 molar, and this is 0.1 molar as well, because the stoichiometry is 1:1:1, right? Simple. 1 mole gives 1 mole, so 0.1 is going to give 0.1. Yeah? Now people try to understand. Imagine this is the hydrogen rod. This is the H2 rod here. And you already know how this H2 rod is made with the help of platinum, right? And the pressure at which H2 was introduced on platinum, that is 10 atm. That is 10 atm, right? Okay. Now guys, try to understand. As per the question, what am I supposed to calculate? Oxidation potential of this hydrogen electrode. This is the hydrogen electrode basically. I need to calculate its oxidation potential. To calculate the oxidation potential, I'll make sure the electrode behaves like the anode. I'll make sure the electrode behaves like the anode. And at anode, oxidation takes place. Tell me, when hydrogen electrode behaves like the anode, oxidation takes place. What has to be the reaction? Few minutes back I told you, H2 gas, it gets converted into what? 2 times H positive aqueous, and with that you'll be writing 2 electrons. This is the reaction which will happen when the hydrogen electrode behaves like the anode, right? Now my dear students, if I ask you how many moles of electrons are exchanged here, you'll say 2 moles of electrons are exchanged. Okay? Try to calculate the QC value. QC value has to be its concentration of H positive raised to the power 2 divided by what? Divided by partial pressure of H2 raised power 1. Now what is the concentration of H positive in the container? The concentration of H positive in the container is nothing, that's 0.1 molar. 0.1 means 10 raised power minus 1. So it's 10 raised power minus 1 raised power 2 divided by. What is the partial pressure of H2? That's 10. So this is 10 raised power minus 2 divided by 10. The value comes out to be 10 raised power minus 3. So you got the QC value. You got the QC value. Now what are we supposed to calculate? Oxidation potential. Use the Nernst equation. Oxidation potential of the half cell is equal to standard oxidation potential. SOP of hydrogen, that's 0. SOP of hydrogen is 0 minus 0.0591 divided by n value is 2 and its log of QC. QC is just 10 raised power minus 3. Again the matter of calculation only. Minus 0.0591 divided by 2. Log of m raised power n is n log m. So minus 3 comes to the front. Log 10 is 1. Just solve it and get the answer in volts. This will be the oxidation potential of this particular half cell when the concentration of HCl in the container is 0.1 molar. Is this clear? Is this clear? Yes, I'll teach everything. Conductance, Kohl-Ross law, everything I'll teach. But that will be in the next session. In this session, I'll be completing complete EMF. EMF part will be completed today. In the next session, Faraday's laws, conductance, Kohl-Ross law, that will be done. All the things clear? Perfect. Let's have a look on one more question. Let's have a look on one more question, yeah? Okay. Look at this particular question. Similar type of question, guys. Similar type of question. You are given with a half cell, right? You are supposed to calculate its oxidation potential. You are supposed to calculate its oxidation potential. Now, oxidation potential you have to calculate. In order to calculate the oxidation potential, you'll make sure that this electrode behaves like the anode. At anode, oxidation takes place. At anode, oxidation takes place. Oxidation means increase in the oxidation state. Oxidation state here is 0. Here the oxidation state is -1. So what should be the reaction? Should I write the reaction as Cl2 gives Cl negative or Cl negative gives Cl2? You tell me that. What should I write? Should I write Cl2 gives Cl negative or Cl negative gives Cl2? Quickly. What should I exactly write? What do you think? What do you think? Since I'm making sure that the electrode behaves like the anode, right? At anode, oxidation takes place. Oxidation means increase in the oxidation state. So through the reaction, I have to show that oxidation state is increasing. So for that purpose, I have to write Cl negative. Cl negative, it gives what? It gives Cl2 gas. Right? So now it becomes -1 to 0. -1 to 0 means -1 to 0 increase in the oxidation state, means oxidation, loss of electrons. Loss of electrons. Now this is Cl2, so this has to be 2 times Cl negative. Tell me one thing. One Cl negative, when it loses one electron, it gets converted into Cl. Now as per the equation, this is Cl2, this is 2, so this has to be 2 as well, right? So you'll be writing 2 electrons with it. You'll be writing 2 electrons with it. I hope this is clear. Okay, so this is the reaction. Now since N value you got, N value is 2, now write the QC. QC is going to be, it's going to be partial pressure of Cl2 divided by concentration of Cl negative raised power 2. What is the partial pressure of Cl2? 10 atm divided by, what is the concentration of Cl negative in the solution? In the solution. Since in the solution you have taken HCl, this HCl would have got dissociated as H positive plus Cl negative. Stoichiometry is 1:1:1, right? So 1 mole of HCl gives 1 mole of Cl negative. 0.1 molar HCl will give 0.1 molar Cl negative, right? So you got the concentration of Cl negative as well. That is simply 10 raised power -1. But this is raised power 2. So it's going to be 10 divided by 10 raised power -2. The value will come out to be 10 raised power 3. So this is QC. Now what do I need to calculate? I need to calculate the oxidation potential of the half cell. So I'll write oxidation potential of the half cell is equal to standard oxidation potential E0x minus 0.0591 divided by, this is going to be N, and now it's going to be log of what? Log of QC. I believe all the terminologies you already have now. So EOX is equal to E0OX. What is E0OX? Standard oxidation potential. Look at this. -1 to 0. -1 to 0. -1 to 0. Increase. Increase means oxidation. So this SOP. And that SOP I need here. So it's -1.36. Minus 0.0591. Divided by N value is 2. Log of 10 raised power 3. Log of 10 raised power 3 means T log 10. Log 10 is 1. Just solve this part. Get the answer of the question. Get the oxidation potential of the half cell, which you were supposed to calculate. Right? Electrons will add. Why electrons will add? At anode, oxidation takes place. Oxidation means loss of electrons. Right? That's why electrons are on right side. Okay? And this is Cl negative. Cl negative. Right? It's not Cl or something. I hope it's clear. Perfect, guys? All right, let's try to solve one more question. Let's try to solve one more question. Look at this particular question. See what the question says. A solution containing 4 into 10 raised power -4 molar Cr2O7 dinegative and 2 into 10 raised power -2 molar Cr tripositive ions shows a pH of 1. Calculate the reduction potential of this half cell. So as per the question, we are given with a half cell, and half cell is like this. Half cell is like this. Platinum solid, Cr2O7 dinegative, right? Cr tripositive. This is your half cell, correct? Now, my dear students, what you need to calculate? You need to calculate the reduction potential of this half cell. You need to calculate the reduction potential of this half cell. In order to calculate its reduction potential, I'll make sure this half cell behaves like the cathode. I'll make sure this half cell behaves like the cathode, because at cathode only reduction takes place, right? Now, try to understand. What is the oxidation state of chromium here? It is +6. Oxidation state of chromium here, it's +3. So +6 to +3. +6 to +3. +6 to +3. Decrease in the oxidation state. Decrease means reduction. And I have to write the reduction reaction only. So basically, Cr2O7 dinegative, aqueous. It has to get converted. It has to get converted into Cr tripositive aqueous. then only I can represent reduction. Because reduction means decrease in the oxidation state. +6 to +3, decrease. Decrease means gain of electrons. Now, when Cr2O7 dinegative gets converted into Cr tripositive, how many electrons are gained? +6 to +3, change is 3. 3 is the change for one atom, but I have 2 atoms of chromium, so 3 2s are 6. I'll say 6 electrons are being gained here, right? And then it gets converted into Cr tripositive. Make sure this is 2 Cr, so it has to be 2 times Cr this side as well. Okay. Now, people, if I ask you whether this particular reaction is balanced or not, look at it carefully. Is it balanced? Look at it carefully. Is it balanced? The reaction is not balanced because you have got oxygen here. No oxygen on this side. There is one hint that is given. As per the question, pH of the solution is given to us as 1. If pH is 1, that means solution is acidic. So, you are going to balance this particular reaction in acidic medium. You are going to balance this reaction in acidic medium. And how do you balance the reaction in acidic medium? 7 oxygen on this side. No oxygen on right side. So, right side is oxygen deficient. So, add 7 water molecules on this side. Now, after this, balance hydrogen. 14 hydrogen on this side. So, it has to be 14 H positives on this side as well. So, now the reaction is balanced. Reaction is balanced. At the same time, if I ask you how many moles of electrons are exchanged, 6 moles of electrons are exchanged in the net cell reaction. Okay. Tell me the value of QC. Start with this particular thing. It is concentration of chromium tripositive raised by stoichiometric coefficient, that's 2. This is in liquid form, its actin-mass unity, nothing to do with that. Divided by, it's going to be concentration of Cr2O7 dinegative raised by stoichiometric coefficient 1. And this is going to be concentration of H positive raised by stoichiometric coefficient, that's 14. So this is how you write the QC expression. Correct? Now tell me one thing. Concentration of Cr tripositive is given, this is given, but concentration of H positive is not given. But pH of the solution is given to me as 1. And you already know, if pH is equal to 1, what does that mean? That means concentration of H positive is 10 raised power minus 1 molar. Right? If pH is X, so concentration of H positive becomes 10 raised power minus X. Right? So, put the values here. Cr tripositive concentration is given to me, I believe, 2 into 10 raised power minus 2. So, 2 into 10 raised power minus 2 raised power 2 divided by concentration of Cr2O7 dinegative given to me as per the equation, 4 into 10 raised power minus 4. Concentration of H positive, 10 raised power minus 1 raised power 14, right? I'll say this particular term gets cancelled out. So the final value is 10 raised power 14. So this is QC. This is QC, right? What was I supposed to calculate? As per the equation, I was supposed to calculate the reduction potential. Now we use the Nernst equation. ERED is equal to E naught RED, standard reduction potential. This is the standard reduction potential which is given. See, nothing is mentioned. Nothing is mentioned. Whenever nothing is mentioned, you'll be assuming it as standard reduction potential. When nothing is mentioned here, right? So assume it as SRP always. So SRP is 1.5 minus 0.0591 divided by n values 6 log of QC. QC value is 10 raised power 14, right? So m raised power n is n log m. So it is going to be 1.5 minus 0.0591 divided by 6 log of m raised power n is n log m. So 14 log 10. Log 10 is 1. So this particular term you have to solve. The answer is going to be in volts. So this is the reduction potential of the half cell which you were supposed to calculate. I hope this is clear to everyone. Let me know once in the chats quickly. Is this clear? Is this clear? Let me know once in the chats quickly, people. Everyone. Everyone. Perfect. Okay. Let's try to solve one more question. Look at this particular question. Read the question carefully first. I want you guys to read the question and let me know in the chats whether you can solve this question or not. Read it. A zinc rod is dipped in 0.1 molar solution of its salt at 25 degrees centigrade. Assume the electrolyte is 20% dissociated. Calculate the electrode potential. They're asking you to calculate electrode potential. They are not mentioning clearly whether to calculate oxidation potential or reduction potential. Whenever this kind of the scenario arises, you are supposed to calculate electrode potential. That means they are asking you to calculate the reduction potential. Okay? They're asking you to calculate the reduction potential. So can't you do it? What do you think? What do you think about this question? Can it be done? Quickly in the chats, can it be done? See guys, look at the questions clearly. Imagine this is the container. And in this particular container, what do we have? We have got salt of a zinc. Let's assume that we have got zinc sulfate. Imagine we have got zinc sulfate. Now tell me how zinc sulfate undergoes dissociation. Zinc di positive plus SO4 di negative, like this. Okay. Now we have introduced a zinc rod here. This is the zinc rod which you have introduced. So zinc rod you have introduced into a solution containing its own ions. So you'll be calling this whole setup as, this whole setup is your zinc electrode, right? Now, as per the question, you have to calculate the reduction potential of the zinc electrode. When? You have to calculate the reduction potential of the zinc electrode when 20% electrolyte is dissociated into its ions. When 20% electrolyte is dissociated into its ions, at that point of time, what will be the reduction potential of this electrode? Now guys, have a look. See, this is time t is equal to 0. At time t is equal to 0, what is the concentration of zinc sulfate that's given to me? The concentration of zinc sulfate is 0.1 molar. So C value is 0.1 molar, right? So this will be 0, this will be 0. Now, if you remember, we have discussed in equilibrium. After some time, this will be C minus C alpha. And this is going to be C alpha, and this is going to be C alpha, right? Do you remember? If this is C minus C alpha, this has to be C alpha, this has to be C alpha. Stoichiometry is 1:1:1. Okay. Now, how much percentage of zinc sulfate should get dissociated? 20%. If 20% is getting dissociated, that means alpha value is 0.2. Alpha value is 0.2. Correct? So tell me, what will be the concentration of zinc di-positives in the container when 20% electrolyte is dissociated? When 20% electrolyte is dissociated, what is the concentration of zinc di-positive in the container? The concentration of zinc di-positive is C alpha. C value is given to us, 0.1. Alpha value will be how much? 0.2. So 0.1 into 0.2 makes it 0.02. Or you can write it as 2 into 10 raised power minus 2 molar. So this is the concentration of zinc di-positive in the container when 20% electrolyte has got dissociated into its ions. I hope this is clear. Now tell me one thing. What are we supposed to calculate? We are supposed to calculate the reduction potential. For the reduction potential to be calculated, we'll make sure that electrode behaves like the cathode, because at cathode only reduction takes place, right? Now what should be the reduction reaction? Reduction means gain of electrons. So I would say the zinc di-positives which are there in the container, they'll collide with the rod, right? The zinc di-positives which are there in the container, they will be colliding with the rod, will be taking 2 electrons from the rod and getting converted into zinc solid. So this has to be the reaction. Now if I ask you how many moles of electrons are exchanged, how many moles of electrons are exchanged? So basically I'm asking you the N value. N value is 2, right? Okay, what about QC value? QC is equal to, start with the product. It's zinc solid. Its active mass is unity. So 1 divided by, it's going to be concentration of zinc di-positive, raised power stoichiometric coefficient. So it is 1 divided by, what is the concentration of zinc di-positive? What do we need to calculate? We need to calculate the reduction potential of the half cell when 20% electrolyte is dissociated. Now tell me one thing. What is the concentration of zinc di-positive when 20% electrolyte is dissociated? That is 0.02, right? That is 0.02. This value comes out to be 50. Right? This value comes out to be 50. So QC value I got. QC value I got. Right? Now if I got the QC value, I'll be simply writing the Nernst equation. Nernst equation says that ERED is equal to reduction potential of the half cell is equal to E naught RED, standard reduction potential. Check this particular value. Is this SRP or SOP? Plus 2 to 0. Plus 2 to 0 means decrease in the oxidation state, reduction. So this is SRP, right? And I need SRP only. So minus 0. So it is minus 0.76. So this is E naught RED minus 0.0591 divided by N value is 2, and it's going to be log of QC. QC value is how much? QC value is 50. 50 can be written as 5 into 10. Okay. So now it's just a matter of calculation. I'm just breaking it a bit. Then calculation part you will do on your own. So this 0.0591 divided by 2. Log of M into N. Log of M into N is log of M plus log of N. Log of 5 is 0.69 plus log of 10 is 1, right? Just do this calculation and get the value of reduction potential of this particular half cell in volts, right? Is this clear? Is this particular question clear to you? Will you be able to solve this sort of a question as well? Someone is saying, sir, what you are doing is not live. I know you're looking at the time. This time is wrong, right? I know it is 7:17 at this point of time, but over here it's mentioning as 6:47. Since long it's like this. Perfect. Okay, let's have a look on one more type of the question. See, if the question is asked in the NEET from the electrode potential, this can be the toughest question which can be asked in the NEET examination, right? Okay, this can be your tough question which can be asked in the NEET examination, because in this question you'll be using the concepts of equilibrium as well. And have a look how exactly this particular question is to be solved. Understand properly. The question is, calculate the reduction potential. Calculate the reduction potential at pH equal to 14. Calculate the reduction potential at pH equal to 14 for this half cell. For this half cell at 25 degrees centigrade. ASP is given. E naught of something is also given. So basically, as per the question, we are given with the copper electrode. We are given with the copper electrode and we need to calculate its reduction potential. Now, in order to calculate the reduction potential, should I make sure this copper electrode behaves like the cathode or anode? I'll make sure it behaves like the cathode, because at cathode only reduction takes place and I'm supposed to calculate reduction potential only, right? So let's assume that this copper electrode is behaving like the cathode. When it behaves like the cathode, what's going to happen? Reduction, right? Reduction means gain of electrons. So I'll say copper dye positives in the solution, they'll be gaining 2 electrons and they will be getting converted into copper solid. This is the reaction which is going to happen. This is the reaction which is going to happen. This is your reduction reaction. This will only happen when the copper electrode behaves like the cathode, right? So I'm making sure that copper electrode behaves like the cathode. Now tell me one thing. What is the N value? N value you already got. What about QC value? QC value is going to be 1 divided by concentration of Cu dye positive. But my dear students, as per the question, do you see anywhere the concentration of Cu dye positive given to us? Do you see concentration of Cu dye positive anywhere given? No, right? So we have to calculate concentration of Cu dye positive with the parameters, from the parameters which are given to us. Whatever parameters are given to us, just use them and get the concentration of Cu dye positive, because we have to write QC. Okay. Now what all things I'll be doing? Have a look. As per the question, pH is given to us as 14, right? Now, if pH is 14, you know at 25 degrees centigrade, pH plus pOH, this value is 14 at 25 degrees centigrade. Must be knowing this, right? If pH is 14, from here, I'll be calculating pOH. pOH will be 0, right? pOH will be 0. If pOH is 0, what will be the OH negative concentration? It's going to be 10 raised power minus 0. That is going to be 1. So OH negative concentration I could calculate from here. But why do I need OH negative concentration? Have a look. My dear students, KSP of COH whole twice is given. Tell me how the COH whole twice will undergo dissociation. The COH whole twice, how it will undergo dissociation? It will undergo dissociation as Cu dye positive plus what? Plus 2 times OH negative. This is how it will undergo dissociation, right? Now, if I ask you to write the KSP expression, can't you write the KSP expression? It's going to be concentration of Cu dye positive raised by stoichiometric coefficient multiplied by concentration of OH negative raised by stoichiometric coefficient. This is how you write KSP expression. Okay. Now, as per the question, is KSP value given? Absolutely, it's given to me as 10 raised power minus 19 is equal to concentration of Cu dye positive raised power 1. What about OH negative concentration? OH negative concentration is given to us as 1 molar. I mean, this was not given, I calculated it. Now, you would understand why did I calculate it, right? Because I was supposed to get the concentration of Cu dye positive. So finally, I got the concentration of Cu dye positive as 10 raised power minus 19 molar. Perfect. Why did we calculate the Cu dye positive concentration? To get the QC. So it's 1 divided by 10 raised power minus 19. So the value has to be 10 raised power 19. Okay. So this is your QC. This is your QC. Perfect. This is your QC. Clear? Since you calculate QC, you have N value. What are we supposed to calculate? We are supposed to calculate the reduction potential. Use the Nernst equation. ERED is equal to E not RED, standard reduction potential. Look at this particular value. Plus 2 to 0. Plus 2 to 0. Decrease. Decrease means reduction. So this SRP only, right? So 0.34 minus 0.0591 divided by N value. N value is 2 and it's log of QC. And QC already, you know, it's 10 raised per 19, right? Yes. So it's done, right? So it is 0.34 minus 0.0591 divided by 2. Log of m raised per n. Log of m raised per n is n log m, right? So it's going to be 19 log 10. Log 10 is 1. Just solve this particular part. Get the answer in volts. That's the reduction potential of the half cell which I was supposed to calculate. Is this clear? Let me know once in the chats quickly if this is super clear to everyone. Yeah? Everyone in the chats, people. Everyone. Everyone means everyone. Quickly. I said, do you need some lectures of organic chemistry as well? Do you need some lecture? Because physical is almost done, right? You almost completed physical chemistry. Tell me in the chats with yes or no. Let me know in the chats with yes or no, quickly. Organic or inorganic? Which one? Organic or inorganic? Which one? I want every one of you to say it. Just write it. It's just going to take 2 seconds to write it. Just write it, what you want exactly. Organic or inorganic? In inorganic chemistry, we have already completed bonding, if you remember, right? Okay. So I'll take some of the chapters of inorganic also. Let's start then inorganic with the first chapter, periodic classification. Okay. All right. Chalo, got it. Let's move on to one more question now. Let's move on to one more question and then we shall be discussing few more concepts. Just a second. Can you solve this particular question? Look at it carefully. Look at this question. Look at this question right now. Look at this question. Look at this question. You're given with a reaction. In this particular reaction, if you observe, 1 electron is gained here. Gain of electrons is a reduction. So this is a reduction, right? This is SRP that's given, right? Calculate the reduction potential in neutral solution. We are supposed to calculate the reduction potential. Now, in this particular question, you are not supposed to write the reaction. The reaction is already given to us, right? So directly do one thing, write QC expression. Write QC expression. Start with the product. It's partial pressure of NO2, raised by its stoichiometric coefficient, that's 1. H2 is in liquid state, nothing to do with that. Divide by concentration of NO3 negative, raised by its stoichiometric coefficient, and its concentration of H positive, raised by its stoichiometric coefficient. Correct? Now, partial pressure of NO2, we already know. How much is that? 1 bar. Divided by concentration of NO3 negative, that's 1 molar, right? What is H positive concentration? Well, H positive concentration is not given in the question, but you are given with the pH. If pH is 7, that simply tells you H positive concentration is 10 raised per minus 7 molar, right? It is 10 raised per minus 7 molar. So this is 1, multiplied by 10 raised power minus 7 raised power 2. The overall value at the end comes out to be 10 raised power 14. So this is your QC. This is your QC, right? If you got the QC value, how many moles of electrons are exchanged? 1 mole of electron and value is 1. Now, write the Nernst equation. So I'll be writing reduction potential of the half cell is equal to E naught RAD, standard reduction potential, which is 0.78 minus 0.0591 divided by n value. N value is 1. Log of QC. QC value is what? QC value is 10 raised power 14. Perfect. So it is 0.78 minus 0.0591, right? It's going to be log of m raised power n, which is 14 log 10. Log 10 is 1. Just solve this equation and get the answer exactly in what? Get the answer exactly in volts. I believe that you can solve each and every question in which you are supposed to calculate oxidation potential and reduction potential of what? Of the half cells, right? So let me know once in the chats. Let me know once in the chats quickly. Let me know once in the chats quickly. Is everything done? So till now, we exactly saw how to write the Nernst equation for half cells and how do we calculate the oxidation potentials and reduction potentials of the half cells under non-standard conditions, right? What are you saying, sir? Rate reaction must be negative. Must be minus change or not chemical. I'm not getting what you're trying to say. Just be clear with the words. I'm unable to understand what you're asking. All right, guys. So let's move on now. Let's move on to one more topic, that is Nernst equation for complete reversible cells. Nernst equation for complete reversible cells. Now guys, try to understand. So till now I was showing you how to write the Nernst equation for half cells, right? Why do we need Nernst equation for half cells? To calculate the oxidation or reduction potential of the half cell under non-standard condition. Now you'll be given with a full cell. Full cell means complete galvanic cell, you mean, right? In which you have got 2 electrodes and both the electrodes are connected externally as well as internally. Perfect. And imagine like this. Let's say this is the salt bridge. On the left side of the salt bridge, there is anode, and the anode is like this, zinc solid. Let's say it gives zinc dipositive aqueous, right? On the right side, there is cathode. So let's say this copper dipositive aqueous, it gives copper solid. So first of all, this is your Daniell cell, right? This is your Daniell cell. Now let me show you how do you, this is your Daniell cell. It's a galvanic cell basically. It's one complete cell in which 2 electrodes are used. It's one complete cell in which 2 electrodes are used basically. Now, the point is, how do we write the Nernst equation for complete cells? Okay. My dear students, why do we need the Nernst equation for complete cells? To calculate EMF of a complete cell under non-standard condition. To calculate EMF of a complete cell under non-standard condition, what do I need? I would need the Nernst equation. How exactly you're going to write it? First thing, I'll be writing the reaction at anode. What will be the reaction taking place at anode? Zinc getting converted into zinc dipositive. 0 to +2. Increase means oxidation. You know it already. You have discussed this. So reaction at anode is like this. Zinc solid. It gives zinc dipositive aqueous. And with that, you'll be writing 2 electrons. This is the reaction at anode. Similarly, if I ask you what about the reaction at cathode? At cathode, reduction takes place. Copper dipositive gives copper solid. So it is copper dipositive aqueous, right? Plus 2 electrons. It gives copper solid. So this is the reaction at cathode. Now, in both the reactions, electrons are balanced. Now you can directly add these 2 reactions. You can directly add these 2 reactions. When you add these 2 reactions, what do you get? What do we get? So 2 and 2 gets cancelled. So my net reaction becomes zinc solid plus copper dipositive aqueous. It gives zinc dipositive aqueous plus what? Plus copper solid. This is the net reaction. This is the net reaction. If I ask you how many moles of electrons are exchanged, you'll directly say 2 moles of electrons are exchanged in the net cell reaction. Now after that, I would want you guys to write the QC expression. QC is going to be concentration of zinc di positive raised power stoichiometric coefficient, that's 1, divided by concentration of Cu di positive raised power stoichiometric coefficient, that's 1. Right? So this is how you get the QC. After you get the QC, then calculate the E naught cell as well. How do you get the E naught cell? That is your E naught of cathode minus E naught of anode. So SRP of cathode minus SRP of anode. SRP of cathode minus SRP of anode, right? Yes. Now, my dear students, after writing all these things, after getting all these things here, after getting all these things, what do I need to write? At the end, I'll be writing the Nernst equation. And Nernst equation I'll be writing in this format. E cell, which is EMF of the cell, under non-standard conditions, is equal to E naught cell minus 0.0591 divided by N, then it's going to be log of QC. The E naught cell, you would have calculated, right? Because E naught cathode, E naught anode, it will be given to us as per the equation, right? So E naught cell we can calculate, N value we can calculate, QC we have calculated. So put all the parameters here and get the value of E cell basically, right? So this is how you use your Nernst equation to calculate EMF of the cell, right? Perfect. Is this clear? Happy birthday, sir. Whose birthday is it? Is it my birthday? I have no idea. So guys, let me know once in the chats. All the things are clear till here? Are all the things clear? Did you get the idea of how Nernst equation is used? All right. So let's exactly try to see some questions through which you'll get the idea how Nernst equation is used for the complete cells. For example, this is the question. This is the question on your screen. Let's see how this sort of equation is to be solved. Calculate the EMF of the cell. You are given with a cell in which you have used two electrodes, right, which are separated with the help of salt bridge. Anode, cathode, right? Now you are supposed to calculate the EMF of this particular cell over here. You are supposed to calculate EMF of the cell. Now, my dear students, it is one complete cell, and you already know how do we calculate EMF of a complete cell. We do it with the help of Nernst equation, and you exactly know the steps to be followed. So first of all, I'll be writing the reaction taking place at anode. Tell me what will be the reaction at anode. So at anode, oxidation will take place. Tin is getting converted into Sn di positive. So I would say Sn solid will be getting converted into Sn di positive aqueous, and with that you'll be writing 2 electrons. This is the reaction at anode. Similarly, reaction at cathode. Pb di positive is getting converted into Pb solid. So the reaction has to be Pb di positive has to get converted into Pb solid, right? So the reaction has to be, I would say, Pb di positive aqueous plus 2 electrons. It has to get converted into Pb solid. So this has to be the reaction at cathode. Now, you got reaction at anode, you got reaction at cathode. If I ask you what about the net reaction? So you'll be directly adding them up. When you add them up, this 2 and 2 gets cancelled out, right? So my net reaction has to be Sn solid plus Pb di positive aqueous. It gives Sn di positive aqueous plus Pb solid. So this is your net reaction. Okay. Now you are going to write the QC expression. So start with the product. It's going to be concentration of Sn di positive raised by stoichiometric coefficient. This is solid, its active mass is 1, divided by. It's going to be concentration of Pb di positive, right, raised by stoichiometric coefficient. Now, as per the question, are we given with the concentration of tin dye positive and Pb dye positive? Concentration of Sn dye positive is given to us as 1 molar divided by concentration of Pb dye positive is 10 raised per minus 3 molar. So the overall value comes out to be 10 raised per 3. So this is QC. So QC you calculated, right? After calculating QC, you'll be calculating E naught cell. How do we get the E naught cell? E naught cell is going to be E naught of cathode minus E naught of anode, right? Now, which one is your cathode and which one is your anode? Cathode is lead, anode is tin, right? So SRP of cathode, SRP of lead, this is the SRP of lead, which is minus 0.13, minus SRP of anode, SRP of tin, SRP of tin is minus 0.14. The value exactly comes out to be how much? 0.01 volt. So this is your E naught cell as well. So you have calculated E naught cell as well. Perfect. Now, my dear students, all the parameters which are needed in the Nernst equation, you have already calculated them. Now you can directly use the Nernst equation. E cell is equal to E naught cell 0.01 minus 0.0591 divided by N value, that's 2. N value is 2 because 2 moles of electrons are exchanged here, right? So N value is 2. So it's going to be divided by N log of QC. QC value is already 10 raised per 3. So finally it has to be 0.01 minus 0.0591 divided by 2 log of M raised per N, which is N log M. So 3 and log 10 is 1, right? So solve this equation, get the answer exactly in volts. So EMF of the cell is going to be this particular term over here. Yeah? Is this clear to everyone quickly? Let me know once in the chats, people. Is it clear? Perfect. Let's try to see a few more questions so that you can master it properly. For example, guys, you have this sort of a question. Look at this particular question carefully. As per the question, this is the salt bridge. On the left side of it, you have got anode. On the right side of it, you have got cathode. So what are we supposed to calculate? We are supposed to calculate EMF of the cell. EMF of this complete cell. EMF of this particular complete cell. So first of all, what I'll be writing? I'll be writing reaction at anode. At anode oxidation takes place. Your anode is your hydrogen electrode. And you know when hydrogen electrode behaves like the anode, this has to be the reaction. H2 gas gives 2 times H positive aqueous plus 2 electrons. So this has to be the reaction. Right? Already discussed. So H2 is getting converted into H positives. So this has to be the reaction at anode. Similarly, reaction at cathode. At cathode, you can see iron tri-positive is getting converted into iron di-positive. So I would say iron tri-positive aqueous will be gaining 1 electron and will be getting converted into Fe di-positive aqueous. Perfect. So this is the reaction at cathode. We got reaction at anode, reaction at cathode. Now if I ask you whether the electrons are balanced in both the reactions or not, the electrons are not balanced yet. So this is 2, this is 1. So it's time to balance the electrons. So multiply this particular reaction by number 2. So this has to be 2 times, this has to be 2 times, even this has to be 2 times. Now, you can add these 2 reactions directly. And when you add these 2 reactions, what do we get? We get something like this. H2 gas plus 2 times Fe tri-positive aqueous. What does it give? It gives 2 times H positive aqueous. And with that, you get 2 times Fe di-positive aqueous. This is your net cell reaction. This is your net cell reaction. Okay. Now, if I ask you how many moles of electrons are exchanged, you directly say 2 moles of electrons are exchanged in the net cell reaction. So write the expression for QC now. Write the expression for QC. Start with the product. It's going to be concentration of H positive raised power 2. And it's going to be concentration of Fe di positive. Concentration of Fe di positive raised power 2 divided by partial pressure of H2 gas raised power stoichiometric coefficient 1. And with it, concentration of Fe tri positive raised power stoichiometric coefficient. Now, concentration of H positive. H positive concentration is how much? 10 raised power minus 3. Raised power 2 comes out to be 10 raised power minus 6. Right? Fe di positive concentration 0.01, which is 10 raised power minus 2. Raised power 2 comes out to be 10 raised power minus 4 divided by partial pressure of H2 gas 10 raised power minus 1. Concentration of Fe tri positive, 0.1. That means 10 raised power minus 1 raised power 2. That means 10 raised power minus 2. So in the numerator, you have got 10 raised power minus 10. In the denominator, you have got 10 raised power minus 3. So the overall value is 10 raised power minus 7. So this is QC. You have got the QC as well. Okay. Since you got the QC, now it is the time to calculate E naught cell. E naught cell has to be equal to E naught cathode, SRP of cathode. So SRP of this particular electrode is a given. Well, it is Fe di positive gives Fe tri positive. So increase in the oxidation state. So this is SOP, but I need SRP. SRP will be 0.17. SRP of cathode minus SRP of anode. Anode is your hydrogen electrode. Its SRP is 0, right? E naught cell is 0.17 volt. Now all the parameters which are needed to write the Nernst equation, we have wrote that. So what I'll be doing now? I'll be using the Nernst equation. I'll say E cell is equal to E naught cell minus 0.0591 divided by N value is 2, and it's going to be log of QC. QC value is how much? QC value is 10 raised power minus 7, right? Now it's just a matter of calculation. 0.17 minus 0.0591 divided by 2. Log of m raised power n is n log m. So minus 7 comes to the front. Log 10 is 1. You can solve it and get the answer exactly in volts, right? I hope this sort of equation you can easily solve again from now onwards. Is it clear? Let me know once in the chats quickly. Perfect, guys. Okay. Look at this particular question. Look at this particular question now. See, guys, the EMF of the cell is given. EMF of the cell is given 0.81 volts. Calculate the charge on the metal. Calculate the charge on the metal. Okay. See what the question says basically. See what the question exactly says. As per the question is concerned, M is getting converted into Mn positive, right? M is getting converted into Mn positive. So basically, as per the question, we are supposed to calculate the charge present on the metal ion, right? We have to get this particular N value, the charge present on the metal ion. Now, again, I'll be using the same procedure, whatever I have been doing till now, same procedure, similar procedure I'll be doing, and definitely you will be able to solve this question as well and see how exactly. First of all, what has to be the reaction at anode? M gives Mn positive. So the reaction has to be M solid. It gives Mn positive aqueous plus how many electrons? Plus N electrons. This is the reaction at anode. Similarly, reaction at cathode, H positive gives H2. So the reaction has to be 2 times H positive aqueous, since hydrogen electrode is behaving like the cathode. And when it behaves like the cathode, the reaction has to be like this. This is your H2. Perfect. So you got the reaction at anode, you got the reaction at cathode as well. Now, my dear students, if I ask you whether the electrons are balanced or not, the electrons are not balanced in both the reactions. Here you have got n electrons, here you have got 2 electrons. So I'll be multiplying this reaction by number 2. I'll be multiplying this reaction by number n, right? So after multiplying, what do I get? This is 2 times, this is 2 times, and this is 2n times. This will be 2n times, right? This will be 2n times. Perfect. And this is also going to be 2n electrons, and this is going to be n times H2. Okay. Now is the time to add these two reactions. When I add these two reactions, what do I get? I get 2 times metal solid plus 2n times H positive aqueous. It gives what? It gives 2 times Mn positive aqueous. 2 times Mn positive aqueous plus n times H2 gas. So this is your net reaction. Now, if I ask you how many moles of electrons are exchanged in the net cell reaction, will you say n or 2n? I'll say 2n moles of electrons are exchanged. I'll say 2n moles of electrons are exchanged in the net cell reaction. Now, tell me one thing, whether you can write the expression for QC or not. Absolutely. It's going to be concentration of Mn positive raised power stoichiometric coefficient 2. This is going to be partial pressure of H2 gas raised power stoichiometric coefficient, that's n, divided by, this is solid, leave it. This is H positive concentration raised power stoichiometric coefficient, that's 2n. So this is how you write QC. This is how you write QC. Now tell me one thing. Whether the concentration of Mn positive is given or not. 0.02 molar, which means 2 into 10 raised power minus 2. Raised power 2 means 4 into 10 raised power minus 4. Right? Partial pressure of H2, that's 1. Concentration of H positive, that's also 1. 1 raised power anything is 1. So QC value I directly got. Okay. Now as per the question, let's try to calculate E naught cell. E naught cell is E naught of cathode. Cathode is your hydrogen electrode. Its SRP is 0 minus SRP of anode. SRP of this particular electrode. Look at this. M gives Mn positive. M gives Mn positive. So 0 to plus N. Increase in the oxidation state means oxidation. So this SOP. But what do I need? I need SRP. So this is minus 0.76. So this value is equal to 0.76 volts. So this is your E naught cell as well. Right? So I believe all the parameters are calculated. Now it is the time to use the Nernst equation. What you'll be writing? You'll be writing E cell is equal to E naught cell. Right? E cell is equal to E naught cell minus 0.0591 divided by N. But here you are not going to use N. Here you will be writing 2N because 2N moles of electrons are exchanged. Then you will be writing log of QC. Correct? So E cell value as per the equation, that's 0.81 is equal. E naught cell is 0.76. So 0.81 minus 0.76. How much that comes out to be? That comes out to be 0.05. Right? 0.05. Now multiply that 0.05 with 2N and divide that with 0.0591 will be equal to minus log of QC. Right? I just simplified things, nothing else. I just simplified the things. So it is going to be 0.1 divided by 0.0591 is equal to minus log of QC. Right? Minus log of QC. I think one term is missing. That's N, right? That's N. QC as per the equation is given to us. QC as per the equation is given to us. How much? QC, I mean, we have calculated QC and where the QC is? QC is 4 into 10 raised per how much? 4 into 10 raised per minus 4, right? Now do one thing. This minus is here, right? This minus, take it on the other side. Take it on the other side. Now, do a bit of calculation now. Log of m into n is log m plus log n. So log of 4 is 0.6 and this is going to be log of 10 raised per minus 4 is, this is going to be minus 4. So this overall value comes out to be minus 3.4. This overall value comes out to be minus 3.4, minus 3.4. So minus gets cancelled out. So n value will be equal to 3.4 multiplied by 0.0591 divided by 0.1. And approximately, this one is 1, approximate calculation. This one is approximately 2. So approximately n value is coming out to be 1.7. But what is n basically? N is the charge on the metal ion, right? So n value is coming out to be 1.7. Can charge be 1.7? Charge cannot be 1.7, right? It has to be the integer. I mean, it has to be a natural number. So which one is the closest natural number? That's 2, right? So I would say n value is coming out to be 2. That means the charge on this metal ion over here. The charge on this metal ion over here has to be exactly 2. So that's something which we were supposed to calculate. Is this clear now? Is this clear to everyone, people? Quickly. Perfect. I believe you can solve these sort of questions from now onwards, okay? I believe you can solve these sort of questions from now onwards. Let's look at one more topic that's again important. What is it? Nernst equation at equilibrium. What is meant by Nernst equation at equilibrium? What is first of all meant by equilibrium stage? Let's try to understand it. My dear students, if you remember, we have discussed Daniell cell long back, right? We have discussed Daniell cell. I'll just use the Daniell cell to make you understand what this equilibrium, what equilibrium conditions exactly are. Try to understand. This is the container, right? This one container. And this is one more container. Over here, which electrolyte you have? You have got zinc sulfate. In this particular container, which electrolyte you have? You have got copper sulfate. In this particular container, you are keeping zinc rod And here you are introducing copper rod. Here you are introducing copper rod. So you have got two electrodes, zinc electrode, copper electrode. Now, my dear students, you are connecting them with the help of what? With the help of emitter, right? And this is your solder bridge. So this cell I'll be calling as the Daniell cell, right? This cell I'll be calling as Daniell cell. And in Daniell cell, we have discussed in Daniell cell, your zinc electrode behaves like the anode and your copper electrode behaves like the cathode. That's something which we know already. We have discussed that, right? We have discussed that. Your copper electrode, it behaves like the cathode. And your zinc electrode, it behaves like the anode. Okay? Now guys, tell me one thing. For the copper electrode to behave like a cathode, right? For the copper electrode to behave like the cathode, can I say SRP of copper should be more than that of SRP of zinc? Because at cathode, reduction takes place. At cathode, reduction takes place. Can I say copper electrode can only behave like cathode if its SRP would have been more? Absolutely, absolutely. Imagine that. I'm giving you arbitrary numbers. Imagine that SRP of cathode here is 5 volts and SRP of anode here was 1 volt. Imagine, just to make you understand things first. Imagine the SRP of copper electrode was 5 volts, the SRP of zinc electrode was 1 volt. Now, which one has got more SRP? Copper. The one which has got more SRP will easily undergo reduction, and the reduction happens at cathode. So your copper is behaving like cathode and your zinc is behaving like anode right now. Okay? Now guys, tell me one thing. Tell me one thing. Well, these are the arbitrary SRP values which I gave you, just to make you understand. Right? Just to make you understand. Just to make you understand. Now tell me one simple thing. When this cell will start working, when the cell starts working, what happens at anode? Oxidation takes place. Oxidation means loss of electron, right? The zinc rod is made up of zinc atoms. The zinc rod, it is made up of zinc atoms, and those zinc atoms will undergo oxidation. Those zinc atoms will get converted into zinc dipositives, and those zinc dipositives will enter into this solution. And when zinc dipositive enter into this solution, at the same time, from the salt bridge, SO4 dinegative will come and neutralize that. So just tell me one thing. When the cell works, when the reactions takes place at anode and cathode, due to the reaction at anode, what is happening to the concentration of zinc sulfate? Is the concentration of zinc sulfate in the left container increasing or decreasing? What do you think? Is the concentration of zinc sulfate in the left container increasing or decreasing? Since in the left container, what's happening? Oxidation. Zinc atoms are oxidized, getting converted into zinc dipositive. That zinc dipositive enters into this container. And when the zinc dipositive enters into the container, at the same time, from the salt bridge, SO4 dinegative will come, will neutralize it. So in the left container, I must say, the concentration of zinc sulfate increases with time, right? The concentration of zinc sulfate increases with time in the left container. Whereas in the right container, what happens? Reduction. Reduction of what? Since in this particular container, you have got two types of ions, copper dipositive, SO4 dinegative. Those copper dipositives will collide with the rod, will take 2 electrons from the rod, will get converted into copper solid, and that copper solid gets deposited on the rod, due to which in this container, the concentration of copper dipositives, in the right container, is it increasing or decreasing? It's decreasing. So eventually I'll say the concentration of electrolyte in the right container is decreasing. So when the cell starts working, the concentration of electrolyte in the left container, that is increasing. Concentration of electrolyte in the right container, that is decreasing. Correct? And a few minutes back, when I taught you Nernst equation, I told you one simple thing. When the concentration of electrolyte increases, reduction potential of electrode increases. Reduction potential of electrode increases. With the increase in the concentration of electrolyte, reduction potential of the electrode increases. With the decrease in the concentration of electrolyte, reduction potential decreases. This is something which I discussed with you a few minutes back. So my dear students, initially the arbitrary value which I gave you, what was the reduction potential of zinc? That was 1 volt. What was the reduction potential of copper? That was, for example, 5 volts. Now when the cell starts working, concentration of electrolyte here increases. If concentration of electrolyte increases in the left container, I would say the reduction potential of zinc will start increase. the reduction potential of zinc will start to increase, right? So the reduction potential of zinc will start to increase when the cell will start working. The reduction potential of zinc will start to increase when the cell starts working, right? So earlier it was 1 volt, now it will increase with time. Similarly, the concentration of copper sulfate in the right container, it decreases. Therefore, the reduction potential of copper will decrease with time. So reduction potential of zinc increase with time and reduction potential of copper that decrease with time. Can I say a stage will come at which the reduction potential of both the electrodes will be same? A stage will arise at which the reduction potential of both the electrodes will be the same, right? Or in general, I'll say a stage will come at which the electrode potential of both the electrodes will be the same. At that point of time, will there be any potential difference between the electrodes? There will be no potential difference between the electrodes. And that particular stage in the cell where the potential difference becomes zero because of same electrode potential of both the electrodes, that particular stage is something which you call as equilibrium stage. I hope you got to know what I exactly said. So what I'm going to conclude, I'll say at equilibrium. At equilibrium, the reduction potential of both the electrodes have become equal. If reduction potential of both the electrodes have become equal, that means their oxidation potentials will be also equal. So in general, I'll say electrode potentials are same. At equilibrium, electrode potentials of both the electrodes will be same. Therefore, the potential difference will be equal to 0. If potential difference is equal to 0, if E cell is equal to 0, delta G for the cell is minus N of E cell, right? If E cell is 0, so delta G for the cell becomes 0. And at this particular point of time, will there be any current drawn from the cell? I'll say no current is drawn from the cell because potential difference of the cell has become 0, right? Potential difference of the cell has become 0. Now, my dear students, if you look at your Nernst equation, if you write your Nernst equation at equilibrium, so first of all, Nernst equation is nothing. That is E cell is equal to E naught cell minus 2.303 P divided by NF. And it used to be log of QC. This was the general form of the Nernst equation. But if I write the Nernst equation at equilibrium, this term becomes 0. And at equilibrium, your QC is replaced by KC or KEQ, you can say. Right? At equilibrium, QC and K are equal. Right? Now, if I write the Nernst equation at equilibrium, you'll be writing it like this. E naught cell is equal to 2.303 RT divided by NF. And then it's going to be log of KEQ. So this is how you exactly write the Nernst equation at equilibrium. This is how you write the Nernst equation at equilibrium. Perfect. So with the help of this Nernst equation at equilibrium, we can calculate E naught cell with the help of this particular expression. We already know how to calculate E naught cell. That's E naught cathode minus E naught anode. That's one way of calculating E naught cell. This is one more way of calculating E naught cell. Just make sure the cell comes at equilibrium. At that point of time, you can write this equation through which you can calculate E naught cell. Right? Now, my dear students, you can use few more things as well. See, if you use T is equal to 25 degrees centigrade, which is 298 Kelvin. Right? If you take the value of F as 96500 coulombs, if R value is taken as 8.314 joules per Kelvin per mole, at that point of time, your Nernst equation looks like this. At that point of time, your Nernst equation, how it looks like, you'll be writing E cell is equal to 0.0591 divided by N. 0.0591 divided by N. Then it's going to be log of KEQ. Right? This is your Nernst equation when the temperature is 25 degrees centigrade. Right? That means 298 Kelvin. So this expression also you can remember. Now, my dear students, there is one more thing. Do you remember I gave you one equation long back that was delta G is equal to delta G naught plus RT ln of QC. This was the equation which I gave you long back. Now, if I write the same equation at equilibrium, at equilibrium, at equilibrium, your delta G is 0 and QC is replaced by what? QC is replaced by KEQ, right? Now, if you write this particular equation at equilibrium, so delta G is 0 and QC is replaced by KEQ. So from this particular equation, what do I get? I get delta G naught is equal to minus RT ln of KEQ, right? This is one more expression. To calculate delta G naught, one of the expression to calculate delta G naught was minus NF E naught cell. So this is one more expression of calculating delta G naught. Well, you can convert it in terms of what? In terms of logarithmic form as well. You can say delta G naught is equal to minus 2.303. This is RT and it's a log of KEQ. Log of KEQ. Perfect. So these are certain expressions which are valid when the cell is at equilibrium, right? Perfect, guys. Is every single thing perfect till here? I believe every single thing is perfect till here, right? Okay, for example, I'm giving you a question. Let me make a question like this. Calculate the equilibrium constant for the following. Calculate the equilibrium constant for the following. Let's say the reaction is like this. Zinc solid plus cadmium dye positive aqueous. Let's say it gives cadmium solid plus zinc dye positive aqueous. Let's say this is the reaction which is given to me. And for example, E naught cell is equal to, let's say E naught cell is equal to, just a second. Let's say E naught cell is equal to 0.46 volts. Okay, you have to calculate equilibrium constant. You have to calculate equilibrium constant. Can you give it a try and solve this question? See guys, first of all, you have to calculate equilibrium constant. Well, in order to calculate the equilibrium constant, this cell has to be at equilibrium. This cell has to be at equilibrium, right? And when this cell attains equilibrium, I'd say E cell is equal to 0. If E cell is equal to 0, at that point of time, you can use the equation which we got a few minutes back only. E naught cell is equal to 0.0591 divided by N, and then it's going to be log of KEQ, right? E naught cell is given. What is N value? N value will be 2 for this reaction. N value is 2. From here, you can easily calculate KEQ. So one equation, one unknown, nothing to do, right? These are very simple equations. Similarly, this is one more simple equation. Similarly, these are basic equations, right? These, I believe, you can do on your own. Calculate delta G for the reaction. When concentration of every ion is 1 molar, temperature is 298 Kelvin. So guys, one thing you have to agree here. If concentration is 1 molar, temperature is 298 Kelvin. Believe the pressure is 1 bar. That means the conditions which are given to us, these are standard conditions. So we have to calculate delta G under standard conditions basically. We have to calculate delta G under standard conditions. And delta G under standard conditions is what? That's basically delta G naught. And delta G naught is what? Minus NF E naught cell. Minus NF E naught cell. So first of all, what do I need to get? I need to get E naught cell basically. I need to get E naught cell. So what is E naught cell? E naught cell is something which is E naught of cathode minus E naught of anode. What is E naught of cathode? That's SRP of cathode minus SRP of anode. Now what is cathode? What is anode? Have a look. This is SRP of tin. This is SRP of copper. Which one has got more SRP? This one has got more SRP, right? Just a second. I think there is something wrong in this question. Yes, the values are not up to the mark. The values are not right. Either the reaction is given in the reverse format, or either the reaction is not right or the values are not right. Just a second. See, copper is getting converted into copper dye positive, so copper has to undergo oxidation, and tin is undergoing reduction. If tin has to undergo reduction, if this Sn dye positive has to undergo reduction, so its SRP should be more, right? SRP of Sn dye positive, this is SRP, this is also SRP. SRP of Sn dye positive should be more, but here it's mentioned as less. So it's a wrong question basically. The values are wrong. Okay? The values are wrong. Perfect? Did you get what I'm trying to say? In the reaction, copper is undergoing oxidation, Sn dye positive is undergoing reduction. For Sn dye positive to undergo reduction, for Sn dye positive to undergo reduction, the SRP of Sn dye positive should be more, but here SRP of Sn dye positive is less. So there is some discrepancy in the values, right? Anyways, leave the values aside. Leave the values aside. I'm just showing you the approach of the similar type of question which can be of this type. E naught cell you will calculate as E naught cathode minus E naught anode. This is SRP of cathode and this SRP of anode. So from here you can calculate E naught cell. E naught cell, F is 96500. N means number of moles of electrons exchanged, right? Here you will get the answer in joules. You'll be dividing with 1000. Then you will be getting the answer in kilojoules. I believe this is clear. I believe this is clear to everyone. Okay? Perfect. So let's do one thing. Let's take a break here for some time. And after the break, we'll get back to the business again. So till what time? Till what time we are going to take the break? It's 8:08. So since it is the dinner time, so break till okay? Every one of you. Every one of you. This is for everyone. Be back on time because we have to complete this EMF part. Right? Well, after the break, it will just take like 1 hour or 1.5 hours, something like that. So let's complete it today only. Why to keep it for the next session? Okay? So be back at 8:35 sharp. Till then, you guys can have your dinner, etc., etc. See you. What's up, people? Are you back? Are you all back? Yeah? Everyone is here or not? Let me know in the chats quickly. Call up everyone. Call up everyone. Let's start. Are you guys done with your dinner, by the way? Are you all done with your dinner? Perfect. So, guys, there is one more important topic which we are going to cover now. That is concentration cells. Okay? Concentration cells. This again one important topic from which question can be asked, right? So let's get to know what exactly these concentration cells are, how many types of concentration cells we have, how do we exactly write the Nernst equation for the concentration cells. Let's get to know about all these things one by one. First of all, in case of concentration cells, what do we do? My dear students, in case of concentration cells, let me tell you a few points, then I'll make you understand one by one. In case of concentration cells, let me tell you two same electrodes are used. Two same electrodes are used. Till now, if you talk about the galvanic cell, in case of galvanic cell, we used to take two different electrodes. We used to connect them externally, we used to connect them internally, then we used to get one complete cell, right? So in the galvanic cells, till now, whatever galvanic cell we have studied, we used to take two different electrodes and connect them. But in case of concentration cells, we are not going to take two different electrodes. We are going to take two same electrodes, right? Point number one. So two same electrodes will be taken in case of concentration cells. Number one. Number two, EMF is, or let me write it like this, EMF of the cell is due to either concentration difference of anode and cathode, or the partial pressure difference, between the anode and cathode. What exactly it means, you'll get the idea in some time. First of all, I would want you guys to take a note of these statements. In case of concentration cell, we'll be using two same electrodes. Now, EMF is generated in case of concentration cells due to either the concentration difference in anode and cathode, or due to partial pressure difference in anode and cathode. What this particular statement means, you'll get the complete information of it in some time. Just wait for it. You just tell me one thing. My dear students, if you are taking two same electrodes, for example, you are taking zinc electrode on one side. This is one more zinc electrode only. So these are two zinc electrodes. You are connecting them externally, you are connecting them internally. So you are getting a cell. If I ask you, if you are using two same electrodes, what will be the value of E naught cell? E naught cell is basically E naught of cathode minus E naught of anode. So SRP of cathode minus SRP of anode. Now cathode and anode, they are same, zinc and zinc. So SRP of cathode, SRP of anode. Since both the electrodes are same, so their SRP values will be also same. So first point which you need to know, that E naught cell, in case of concentration cells, do remember this particular value will be equal to 0. This particular value will be equal to 0, right? So in case of concentration cells, I'll be using two same electrodes, right? If you are using two same electrodes, you are connecting them externally as well as internally. You are getting a complete cell. Now, what about E naught cell for this particular complete cell? What about E naught cell for this cell over here? I would say E naught cell will be equal to E naught cathode minus E naught anode. Now, cathode, anode both are zinc electrodes. Their SRP value is same, right? So SRP of cathode, SRP of anode will be the same because both are zinc electrodes. So E naught cell will be equal to 0. So do remember, whenever from now onwards, you will see two same electrodes connected externally and internally, the first point which should come into your mind, that is the E naught cell value will be equal to 0. Okay. Now guys, let's try to analyze this a bit more in detail. But before that, let me tell you one more point. Try to understand what exactly I'm going to say. Okay. Have a look, people. Have a look and understand. In order to understand these concentration cells in detail, let me first of all tell you, we divide these concentration cells into two categories. One is going to be electrolytic concentration cell, which we have to discuss in detail. The second one is going to be electrode concentration cell. Both these cells are to be discussed in detail. But right now, I'm just giving you the idea of few things which you are going to remember. In case of electrolytic concentration cells, what do we do? The concentration of anode and cathode. The concentration of anode and cathode are kept different. The concentration of anode and cathode are kept different. But in case of electrolytic concentration cells, in case of electrode concentration cells, partial pressure of what? Partial pressure of anode and cathode. Partial pressure of anode and cathode are kept different. Right? In case of electrolytic concentration cells, concentration of anode and cathode will be kept different, but do remember, partial pressure of anode and cathode will be kept same. Here, partial pressure of anode cathode will be kept different, but concentration of anode cathode will be kept same. This is the point which I want you guys to take a note of first of all. Now it is the time to discuss these concentration cells in detail, my dear students. Okay. So our first topic right here is going to be electrolytic concentration cell. So mark the heading as electrolytic concentration cell. Electrolytic concentration cell. This is the first important topic. Have a look, people. First of all, in case of electrolytic concentration cells, what do I exactly do? I'll be taking two same electrodes. Let me represent it over here. Imagine that this is one container. This is, for example, one more container. In this particular container, let's say we have got Mn positive ions. In this particular container also, we have got Mn positive ions. Let's assume the concentration of Mn positives in the left container is C1 molar. Let's assume the concentration of Mn positive in the right container is, for example, C2 molar. Okay. Now, my dear students, here what exactly I'm going to do? I'm keeping a metal rod. Here also, what am I doing? I'm keeping a metal rod. So if I ask you whether the electrodes which I have taken, whether these electrodes are same or different, these are same electrodes This is M electrode. This is also M electrode. Now, my dear students, I am going to connect these externally with the help of emitter, right? And here you are introducing a salt bridge. So what did we get? We got one complete cell which is made up of two half cells, right? Whenever you see this kind of the cell, whenever you see this kind of the complete cell in which two same electrodes are used, you'll be first of all calling it as the concentration cell. And in case of concentration cells, your E naught cell value has to be right now 0, right? Now, which type of concentration cell this is? My dear students, no doubt you have taken two same electrodes. Where is the difference? The difference lies in the concentration of electrolytes. Whenever you have such type of the concentration cell in which the concentration of anodic and cathodic container is different, you will be calling this particular cell, you will be calling this particular concentration cell as the electrolytic concentration cell. Okay. Now the first point, how do I represent this cell? My dear students, this is the salt bridge. On the left side of the salt bridge, I'll be writing the anode. At anode, your M solid is getting converted into Mn positive. And the Mn positive concentration in the left container, how much is that? That is C1 molar, right? Similarly, on the right side of it, I'll be writing the cathode. At cathode, your Mn positives will get converted into M solid. So Mn positives which were there in the right container, whose concentration was C2 molar, right? They will be getting converted into M solid. Perfect. So first of all, this is how you represent the electrolytic concentration cell, in which two same electrodes are used, but only difference is their concentration is different, right? This is your electrolytic concentration cell. Now, my dear students, the point is, what condition should be followed? What condition this particular cell has to follow so that it can behave like a normal galvanic cell? What kind of condition it has to follow? Let's try to make that condition. Which electrolytic concentration cell has to follow so that it can behave like the galvanic cell, right? So that it can work basically, so that it can produce current basically. Okay. Now try to understand. First of all, for this particular cell to be working, what should happen? At anode, oxidation should happen, right? So first of all, what has to be the reaction at anode? At anode, your M should get converted to Mn positive. So the reaction at anode has to be M solid should get converted into Mn positive with concentration C1 plus N electrons. This has to be the reaction at anode. Now similarly, what should be the reaction at cathode? What do you think? What should be the reaction at cathode? At cathode, reduction should take place. Mn positive should get converted into M. So the reaction has to be Mn positive aqueous with concentration C2 molar. It should gain N electrons and should get converted into M solid. Right? These are the two reactions which should happen first of all. Reaction at anode, reaction at cathode. Now, if I ask you whether electrons are balanced in both the reactions or not, just check it out. If I ask you whether electrons are balanced in both the reactions or not, absolutely in both the reactions, electrons are balanced. When you add them up, N electrons will get cancelled out. This M solid will get cancelled out. So what will be my net reaction? My net reaction here is Mn positive with the concentration C2. It should get converted into Mn positive with the concentration C1. So this has to be my net cell reaction. Okay. Now, my dear students, if I ask you what about the QC value? QC is going to be concentration of Mn positive, that is C1, divided by concentration of Mn positive, that is C2. C1 divided by C2. Simple. If I ask you what about the E naught cell value? E naught cell value will be equal to 0 only because we are using two same electrodes, right? Now comes a point. See guys, if I write Nernst equation for this electrolytic concentration cell, how the Nernst equation looks like? You will write E cell is equal to E naught cell. E naught cell is 0, right? Minus 0.0591 divided by N, and it's going to be log of QC. And QC is just C1 divided by C2, right? You can do one more thing. You can write the same equation like this as well. You can write E cell is equal to multiply this minus with this log it becomes 0.0591 divided by n. Now it becomes log of C2 divided by C. Right? Now it becomes log of C2 divided by C1. Now, my dear students, if you remember, I have told you in the last session, if you remember, for any complete cell to be working, for any complete cell to work like a normal galvanic cell, its E cell value should be positive. Then only delta G will come out to be negative. Right? We have discussed that in the last session. So for this particular cell to be working, I'll write for this particular cell to be working, E cell value has to be, E cell should be greater than 0. Right? E cell should be greater than 0. Then only this cell will be working. Then only this cell is going to produce current. Then only this cell is going to behave like a normal galvanic cell in which current will go from cathode to anode. Right? Perfect. Now guys, the point is when this E cell value will come out to be positive, E cell value will only be positive if log of C2 divided by C1 will be positive. Now the point is when this log of C2 by C1 will be positive, log of X is positive when X is greater than 1. So log of C2 by C1 will be positive when C2 divided by C1 is greater than 1. Right? Which is only possible if C2 is greater than C1. If C2 is greater than C1. So my dear students, if you try to analyze things properly, can I say I got to know something really interesting here? I'll write for an electrolytic concentration cell. For an electrolytic concentration cell to be working. For an electrolytic concentration cell, just a second. For an electrolytic concentration cell, I'll write involving which electrodes? Metal, metal ion. Involving metal, metal ion electrode. For the electrolytic concentration cell involving metal ion electrodes to be working like a normal galvanic cell. In which current is from cathode to anode. To be working like a normal galvanic cell. C2 value should be greater than C1. What is C2? C2 was the concentration of electrolyte in cathode. C1 is the concentration of electrolyte in anode. So I'll say concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. This is the condition which the cell has to follow, which this electrolytic concentration cell has to follow. Then only I can say its E cell value is positive. Therefore, the cell will be behaving like a normal galvanic cell, which electrons will move from anode to cathode and current will shift from cathode to anode. Is this point clear to everyone? Let me know once in the chats. Is this clear to everyone? So this is the first question which is asked. What is the question? The question is for the electrolytic concentration cell involving metal ion electrodes to be working like a normal galvanic cell, the concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode, which is obvious also. If the concentration of electrolyte in cathode is more, since you are using two same electrodes, right? If you are using two same electrodes, how come potential difference will generate here? Potential difference will only generate if concentration of electrolyte in cathode is more, right? If the concentration of electrolyte in this container is more. Why is that? Because more the concentration, more the reduction potential. So this concentration should be more, this concentration should be less. If this concentration is more, that means reduction potential of this electrode is more and reduction potential of this electrode is less. If reduction potential of this electrode is more, this electrode is less. That means potential difference again got created. And whenever there is potential difference, current will be there, right? Then only I'll say the current will shift. Current will show its direction from cathode to anode, right? It's obvious. In case of normal galvanic cell, the direction of current is from cathode to anode. Now, how come this particular cell will behave like a galvanic cell? If the direction of current will be from cathode to anode, when can be the direction of current from cathode to anode? If this particular electrode behaves like the cathode, when this electrode behaves like the cathode, if its reduction potential is more, when its reduction potential will be more, when the concentration of electrolyte in this container is kept more. As simple as that. Okay, so this was our first point. Now comes the second point. In electrolytic concentration cell, there is something called as electrolytic concentration cell involving hydrogen electrodes. There is one special type of cell which is what you call as electrolytic concentration cell involving what? Involving hydrogen electrodes. Now, what this cell exactly looks like? Let's have a look. See guys, imagine that you have taken two hydrogen electrodes. You have taken two hydrogen electrodes, okay? You have taken two hydrogen electrodes. It is just the difference in the electrolytic concentration is different, but the partial pressure of hydrogen gas is same. So let me quickly represent this particular cell directly. So this is salt bridge. On the left side, it's going to be anode. So H2 gas at the pressure of, for example, P bar gets converted into H positive, gets converted into H positive aqueous, right? Whose concentration, for example, is C1 molar. And this is platinum solid here. So this is your anode. Similarly, your cathode. In your cathode, H positive aqueous, whose concentration is C2 molar, it will be getting converted into H2 gas, whose pressure is P bar again. And here also, I've used platinum solid, right? So let me quickly show it to you also. This is, for example, your one hydrogen electrode. This is one more hydrogen electrode. Here you have got H positives with concentration C1. Here also you have got H positives with concentration C2 molar, right? Here you have kept hydrogen rod, H2 rod, and you already know how this H2 rod is made. Here is H2 rod. The partial pressure, the pressure at which H2 was introduced, here, that was P bar, and here also the pressure is P bar only. Perfect. Now you're connecting them externally with the help of emitter and internally with the help of salt bridge. So I got a complete cell. In this particular complete cell, tell me one thing, whether the electrodes are same or different. Electrodes are same, so it's a concentration cell, right? Now, are the concentration of electrolytes same or different? Concentration of electrolytes is different. So it is electrolytic concentration cell involving which electrodes? Involving hydrogen electrodes, right? That's the topic which you wrote. Electrolytic concentration cell involving hydrogen electrodes. Now let's get to know when this particular cell will be working. Let's make a condition which this particular cell has to follow such that this particular cell works like a normal galvanic cell. So let's try to frame that condition. First of all, for this particular cell to be working like a normal galvanic cell, at anode what should happen? Oxidation. So first of all, the reaction at anode should be H2 gas, whose pressure is P bar, right? H2 gas, it will get converted into 2 times H positive, whose concentration is C1 plus 2 electrons. This has to be the reaction at anode. Similarly, what should be the reaction at cathode? At cathode, reduction should take place. H positive should get converted into H2. So the reaction has to be 2 times H positive, whose concentration is C2 molar, right? It should gain 2 electrons and it should get converted into H2 gas, whose pressure is how much? Whose pressure is again P bar only. So this has to be the reaction at cathode. This has to be the reaction at anode. This has to be the reaction at cathode. What should be the net reaction? Just add these two reactions. My dear students, when you add these two reactions, which all things will get cancelled out? 2 electrons cancelled, right? Okay, H2 cancelled because their pressure is same. So my net reaction has to be 2 times H positive with the concentration C2 molar. It gives 2 times H positive with the concentration C1 molar. This is my net reaction. In this particular net reaction, if I ask you how many moles of electrons are exchanged in the net cell reaction, you will say N value is equal to 2. If I ask you what about the QC value, QC has to be concentration of H positive, that is C1 raised power 2 divided by C2 raised power 2. So it is C1 divided by C2 whole raised power 2. This is your QC. Since two same electrodes are used, so it's a concentration cell. In case of concentration cells, E naught cell value is taken to be 0. Perfect. Now, my dear students, after this, what exactly am I going to do? What exactly am I going to do? I'll be using now the Nernst equation. And in case of Nernst equation, I'll say E cell is equal to E naught cell. E naught cell is 0 already. Minus 0.0591 divided by N. What is N value? N value is 2. And here it is log of QC. And QC is nothing, that is C1 divided by C2 raised to the power 2. Correct? I believe everything is clear till here. Now, dear students, try to understand few more things. I'll write something like this. E cell is equal to minus 0.0591 divided by 2 log of m raised power n, which is n log m. So 2 comes to the front. It is log of C1 divided by C2. So 2 and 2 gets cancelled out. So you will be writing E cell is equal to minus 0.0591. It is log of m by n now, which is log of m minus log of n. Right? Log of m minus log of n. Okay. Now, if I ask you what is the C1 and what is the C2, see guys, it is minus 0.0591. Log of C1. What is C1 exactly? C1 is the concentration of H positive in anode, right? Minus log of C2. C2 is the concentration of H positive in cathode, right? C2 is the concentration of H positive in cathode. Now, if I further solve it, I'll be getting something like this. E cell is equal. See, take this minus inside. It's going to be 0.0591, right? Now, it is minus log H positive. Minus log H positive means pH, but this is pH of anode. Similarly, this is minus in the middle. Take this minus inside. So, minus log of H positive, which is going to be pH. So, it's pH of what? It is going to be pH of cathode. So, this is the general expression, my dear students, which you are going to remember from now on. This is something which you are going to remember from now on. And this particular equation to calculate E cell, it is valid for all the electrolytic concentration cells, which involves the hydrogen electrodes. Okay. Now, what exactly were we supposed to do? We were supposed to form a condition which this cell should follow such that it behaves like a normal galvanic cell. And in case of normal galvanic cell, the current is from cathode to anode, right? So for this particular cell to be working, like a normal galvanic cell, right, in which the direction of current is from cathode to anode, for this particular cell to be working, I'll say E cell value should be greater than 0. E cell value will be only greater than 0 if pH of anode will be greater than that of pH of cathode, right? So I will say for the cell to be working, like what? Like a normal galvanic cell. Like a normal galvanic cell. For a cell to be working like a normal galvanic cell, I would say pH of anode should be greater than that of what? It should be greater than that of pH of cathode. Then only the difference between the two will come out to be positive. Then only E cell will be positive. Once E cell is positive, I'll say delta G is negative. If delta G is negative, cell reactions will be spontaneous. If cell reactions are spontaneous, that means that anode oxidation will happen, at cathode reduction will happen, electrons will move from anode to cathode, and current will show its direction from cathode to anode, right? So for this particular cell to be working, do remember pH of anode should be greater than that of pH of cathode. Is this clear to everyone? Let me know once in the chats quickly. Let me know once in the chats quickly. Tell me the answer of this particular question. Tell me the answer of this particular question. What do you think? What do you think about this one? Look at this particular cell. On both the sides, you have used zinc electrode, right? So electrodes are same. So it's a concentration cell, number one. Now, which type? Concentration of zinc dye positive here is C2. Here the concentration of zinc dye positive is C1. So concentration is kept different. So it is electrolytic concentration cell. It is electrolytic concentration cell involving which type of electrodes? Involving metal ion electrodes. Metal ion electrodes. Now, this particular cell, few minutes back only we have discussed this in detail. Now, look at the options. Look at the options carefully. Choose the correct option. The cell reaction will be spontaneous if C1 is greater than C2. Now, a few minutes back only I told you, for the electrolytic concentration cell involving metal ion electrodes to be working like a normal galvanic cell, the concentration of electrolyte in cathode should be greater than that of anode. What is the concentration of electrolyte in cathode? It is C1, right? So C1 value should be greater than C2. C1 value should be greater than C2. Absolutely. C1 value should be greater than C2. Then only this particular cell will behave like a normal galvanic cell in which the direction of current will be from cathode to anode, right? So this particular statement is correct. Cell reactions will be spontaneous, right? It's simple, it's evident. If C1 is greater than C2, C1 here is concentration of electrolyte in cathode, C2 is concentration of electrolyte in anode. If concentration of electrolyte in cathode is greater than that of concentration of electrolyte in anode, then only E cell will come out to be positive. And once E cell is positive, delta G is negative. If delta G is negative, cell reactions are spontaneous. It will behave like a normal galvanic cell, right? So first option is correct. Second, if C2 is greater than C1, if C2 is greater than C1, current will flow from cathode to anode. This is not correct. This is not correct. For the current to flow from cathode to anode, that means for the cell to be working like a normal galvanic cell, concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. So this cannot be the answer. Look at the next one. If C1 is greater than C2, if C1 is greater than C2, cathode concentration greater than anode concentration, current will flow from cathode to anode. Absolutely, it will work like a normal galvanic cell, correct? If C1 is equal to C2, if C1 is equal to C2, my dear students, if C1 is equal to C2, that means C2 by C1 value will be equal to 1. If C2 by C1 is 1, so log of 1 is 0. If log of 1 is 0, that means E cell is 0. If E cell is 0, there will be no current, right? The cell will not work. The cell will not work. This also correct. Done? Is this clear? Is this particular concept clear to you? Let me know quickly in the chats. Is this particular concept clear? See, few minutes back only I told you, I gave you this particular result, right? This was your electrolytic concentration cell involving metal and electrodes. If C1 and C2 are equal, if C1, C2 are equal, so log of 1 is equal to 0. Therefore, E cell is 0. Once E cell is 0, that means the delta G is 0. So leave that part aside. Okay? I believe every single thing is clear till here. Okay. Just a second. Look at this particular question. Look at this particular question. What do you think about this one? First of all, try to identify which cell this is. Are you using two same electrodes? Absolutely two same electrodes. So concentration cell. Now which type? Electrolyte concentration? Electrolyte concentration different. Electrolyte concentration different. So believe it, it is an electrolytic concentration cell. Partial pressure is same. Partial pressure is same. So it is absolutely electrolytic concentration cell involving which electrodes? Involving hydrogen electrodes. Do you remember? Few minutes back only we have discussed this. Electrolytic concentration cell involving hydrogen electrodes. Its E cell is equal to 0.0591 multiplied by pH of anode minus pH of cathode. Few minutes back only we have discussed it, right? What we have to calculate? We have to calculate X. So pH of anodic container we have to calculate. Okay. What is E cell value? It is 0.2364 is equal to 0.0591. pH of anode is X, needs to be calculated. pH of cathode. In the cathode, what is the H positive concentration? That's 1 molar. So I'll say pH of cathode is equal. P stands for minus log. So minus log of H positive concentration of cathode. So which is minus log of H positive concentration of cathode is 1 molar. So the value is 0. So this particular value is 0. So X value from here will be equal to 0.2364 divided by 0.0591. The value will be approximately equal to 4. Right? So what was this X? X was the pH of the anodic container, which we were supposed to calculate. Is this clear to everyone? Is this particular point clear to everyone? Let me know once in the chats quickly. I'll be giving you one question here as the homework, right? I'll be giving you one question as the homework. Look at the question carefully, but be careful with this one. In this one, concentrations are different and partial pressures are same. Concentration is different, partial pressure is same. Or let me solve this question, wait. Let me solve this question. Have a look. See what the question exactly is. The question is, as far as this particular question is concerned, this is your solid bridge. On the left side of it, you are using anode. On the right side, you are using cathode, right? You are using anode and cathode. Perfect. Now try to understand and analyze things. We have to calculate E cell and we have to comment on spontaneity. How can we comment on spontaneity? Spontaneity we can comment only when we have the E cell value, right? So first of all, it's time to get the E cell, and if E cell is positive, that means delta G is negative, cell reactions are spontaneous. This cell will be working like a normal galvanic cell. If E cell is negative, delta G is positive, cell reactions are non-spontaneous. Okay. So first of all, you have used same electrodes and both are hydrogen electrodes in which concentrations are different, partial pressure is same. So this is again electrolytic concentration cell involving hydrogen electrodes, right? How do we calculate its E cell? Its E cell is equal to 0.0591 multiplied by pH of anode minus pH of cathode, right? So first of all, let's calculate pH of anode. pH of anode is going to be minus log of H positive ion concentration in anode. Now, what is H positive ion concentration in anode? In anode, you have used H2SO4. In anode, you have used H2SO4, which would have got dissociated as 2 times H positive plus SO4 dinegative. The concentration of H2SO4 you have kept as 0.05 molar. 0.05 molar initially. So this would have been 0, this would have been 0. Now this H2SO4 would have been completely dissociated. So this is 0. Now 1 mole gives 2 moles. 0.05 will give 0.1 molar. This is going to be 0.05 molar. So I would say the concentration of H positive in the anodic container, that is 0.1 molar. So calculate the pH of the anodic container. pH of anode is minus log of H positive of anode. H positive concentration of anode is 10 raised power minus 1 molar. Value is 1. So pH of anode is 1. If pH of anode is 1, now calculate the pH of cathode. pH of cathode is going to be minus log of H positive concentration of cathode, which is minus log. What is H positive of cathode? It is HCl. In cathode, you have used HCl. So HCl would have dissociated as H positive plus Cl negative. 1:1:1 stoichiometry. So I can say 1 mole of HCl gives 1 mole of H positive. So 10 raised power minus 3 will give 10 raised power minus 3 only. So concentration of H positive in cathode is 10 raised power minus 3 molar only. So the value comes out to be 3. So you calculated the pH of anode, you calculated the pH of cathode, right? You calculated the pH of anode, you calculated the pH of cathode. So this value is 1, this value is 3. So 1 minus 3, the value will be overall what? The value will be overall negative. So first of all, you calculated E cell. After calculating E cell, then you got the sign of E cell as well, which is negative. And you know when E cell is negative. You know when E cell is negative. At that time, delta G will be positive. If delta G is positive, I'll say cell reactions. Will they be spontaneous or non-spontaneous? I'll say cell reactions will be non-spontaneous. Will this particular cell be working like a normal galvanic cell? This particular cell won't be working like a normal galvanic cell, right? Is this clear? Is this clear, people? Quickly in the chats. Quickly let me know in the chats, everyone. Everyone in the chats, quickly. All right. Now, we have got one more concentration cell. What is that? That is electrode concentration cell. Do you know what is electrode concentration cell now? In case of electrode concentration cell, we'll be keeping the concentration same in anode and cathode, but we'll keep the partial pressures different. For example, I'm making the cell here. I'm writing first of all platinum solid, right? And here I'm writing, let's say, H2 gas, whose partial pressure is P1. It gets converted into H positive, whose concentration is, for example, C molar. This is the salt bridge. On the right side, I'll be writing cathode. Let's say in the cathodic container, there are H positives, whose concentration is C molar, right? That is getting converted into H2 gas. And the partial pressure of H2 gas here, I'm keeping as P2 bar. And here I'm using again the platinum solid. Look at this particular cell carefully. In this particular cell, again, you are using two same electrodes. Again, you are using two same electrodes. So it is the concentration cell. Its E cell has to be 0. Now, Is the concentration same or different? The concentration is same, but partial pressure is different. Whenever you see this kind of the cell, in which you will be using two same electrodes, concentration of anode and cathode will be same, but partial pressure will be different. My dear students, you will be calling this particular cell as electrode concentration. Now, what condition this cell has to follow so that it can behave like a normal galvanic cell, so that the direction of current will be from cathode to anode, so that the cell reactions will be spontaneous. Let's try to make those conditions as well. So, for this particular cell to be working like a normal galvanic cell, what should be the reaction at anode? At anode, oxidation happens. H2 is getting converted into H positive. So I'll say H2, whose pressure is P1, it has to get converted into 2 times H positive, whose concentration is C molar plus 2 electrons. This has to be the reaction at anode. Right? Similar reaction at cathode. H positive has to get converted into H2. So at cathode, reduction has to happen. So 2 times H positive with the concentration C molar, it has to gain 2 electrons. Then only it will be getting converted into H2 gas, whose pressure here is P2 bar. Right? So you wrote the reaction which has to happen at anode and cathode. Now, are the electrons balanced? The electrons are balanced in both. My dear students, if electrons are balanced, you can directly add these two reactions. And when you add these two reactions, what is the net reaction? Which all terms will it cancelled out? 2H positive cancel because their concentration is same, right? So my net reaction is going to be H2 with partial pressure P1. It gives H2 with partial pressure P2. Now tell me how many moles of electrons are exchanged? I'll say 2 moles of electrons are exchanged in the net cell reaction. Okay, N values 2. Now if I ask you what about QC? QC value is going to be, start with the product. It is partial pressure of H2 here, which is P2, divided by partial pressure of H2 here, that is P1. So QC we got. Since it's a concentration cell, so its E naught cell value has to be 0. Now, my dear students, one more thing. E naught cell has to be 0. We got to know that. Now, write the Nernst equation. E cell is equal to E naught cell, that's 0, minus 0.0591 divided by N value. N value is 2. Log of QC. QC is nothing, that is P2 divided by P1. P2 divided by P1. I believe it's clear till here. Now tell me one simple thing. If I multiply this minus with this log, what I'll be getting exactly? I'll be getting E cell is equal to 0.0591 divided by 2. It's going to be log of P1 by P2. It's going to be log of P1 divided by P2, right? So this is the result which I got till now. This is the result which I got for E cell. Now, for this electrode concentration cell to be working like a normal galvanic cell, its E cell should be also greater than 0, right? So E cell value should be greater than 0. Then only this cell will be working like a normal galvanic cell. Then only the cell reactions will be spontaneous. Then only electrons will move from anode to cathode. Then only current will go from cathode to anode, right? So E cell has to be greater than 0. Because if E cell is 0, then only delta G for the reactions will be negative. Then only I'll say the cell reactions are spontaneous. Now tell me one thing. When this particular E cell will be greater than 0? I'll say E cell will be only greater than 0 if this particular term is greater than 0. When will be log of P1 by P2 greater than 0? When will be log of P1 by P2 greater than 0? When P1 divided by P2 value will be greater than 1. That means when P1 will be greater than what? Then P1 will be greater than P2. What was P1 and what is P2? Look at it carefully. P1 was the partial pressure of anode and P2 is the partial pressure of cathode. So can I say something like this? For the above cell, which is basically gas ion cell. It is basically, the cell name is for the above cell involving, let me write it like this, for the above cell involving which electrodes? Involving gas ion electrodes, right? For the above cell involving gas ion electrodes to be working like a normal galvanic cell. That means for its cell reactions to be spontaneous, P1 should be greater than P2. P1 is the partial pressure of anode. Directly say partial pressure of anode has to be greater than that of partial pressure of cathode. Partial pressure of anode has to be greater than that of what? It has to be greater than that of partial pressure of cathode, right? This is the condition which the cell has to follow. Then only the cell reactions involved in the cell will be spontaneous. Is this clear? Is this clear to everyone? Let me know once in the chats quickly. Let me know once in the chats quickly. Quickly, guys. Quickly. Look at this question. Will you be able to solve this question? Only thing here is, see, pressure is 2 atm, here it's 1 atm. So pressure is different. Concentrations are also different. So you won't be using any formula directly. You'll be using the general procedure. You'll write the reaction at anode, reaction at cathode, net reaction. Then you'll get the actual QC, right? Actual QC. E naught cell is 0. Then you'll be using the Nernst equation. You'll be at the end getting E cell. And if E cell comes out to be positive, cell reactions will be spontaneous. If they come out to be negative, they'll be non-spontaneous. Is this clear? Is this clear to you? Will you be able to solve this question, or you want me to solve this question? Do you want me to solve this question, or you will be doing it on your own? Because it's a simple question. Nothing different or difficult to do here. Let me know quickly. Will you be solving this question? Let's say yes or no in the chats quickly, yaar. So I would want its answer in the comment section then. If you guys are saying that you will solve it, then right after the session, I would want its answer in the comment section. And I'll exactly see who all are the ones who will at least try this question, right? Then answer can be right or wrong, leave that part aside. At least trying part, I want you guys to do. Okay? Danir, every book is best when it comes to PYQs, because PYQs are same everywhere. Whatever book you want to consult for PYQs, right? On every book, PYQs will be same only. What kind of question this is? Which book is best for PYQs? Every book is best for PYQs, right? Because PYQs, they'll never change, whatever publication you have. Got it? I think you asked the same question yesterday in the J channel as well. Yeah? Guys, one last topic in the EMF part. One last topic in the EMF part. What is that? One last topic in the EMF part, that is thermodynamics of the cell. That is thermodynamics of the cell. They can ask a question related to thermodynamics of the cell as well. What does that mean? They can ask you, calculate delta G for the cell, which already you know, right? How to do. They can ask you, calculate entropy change. They can ask you, calculate enthalpy change. These are the three things which they can ask you related to thermodynamics part of the cell. They can ask you, when the galvanic cell is working, what will be the delta G for the galvanic cell? What will be the entropy change, right? What will be the calculate the entropy change, right? Calculate the enthalpy change. These are the three things which they can ask. Now, how to deal with these three things? How do we get them? My dear students, if you remember, in thermodynamics, I've given you one equation. If you remember, the equation was like this. Dg is equal to VdP minus SdT. Do you remember this equation? And I had told you this particular equation is valid only for reversible processes. It is valid only for the reversible process. When I taught you Gibbs free energy variation with pressure and temperature, when I asked you the Gibbs free energy variation, when I taught you the Gibbs free energy variation with pressure and temperature, at that point of time, I used this particular equation. Ag is equal to VdP minus SdT. My dear students, if I write the same equation at constant pressure, at constant pressure, can't I say dP value is 0? Change in pressure is 0. If dP is 0, I'll say dG is equal to minus S dt. But my dear students, when it comes to reactions, in case of reactions, we do not define entropy. We define entropy change for the reaction, right? In case of reactions, we do not define Gibbs free energy. What do we define? We define Gibbs free energy change for the reaction. In case of what? In case of reactions. In case of reactions, you do not define entropy, you define entropy change of the reaction. Similarly, you define what? You define Gibbs free energy change of the reaction. Okay? Now, for a particular reaction, instead of this particular equation, I can write D of G. Instead of G, I'll be writing delta G for the reaction is equal. It's going to be minus, instead of S, it's going to be delta S for the reaction multiplied by what? Multiplied by dt. Perfect. Now, why am I doing exactly all this? Why am I doing all this? See, guys. See, try to understand what exactly we'll get here. Can I write something like this? Just a second. Okay, can I write D of delta G for the reaction? D of delta G for the reaction divided by dt. It comes out to be equal to minus delta S for the reaction. Okay. Now tell me one thing. What about delta G for the reaction? That is minus NF E cell, right? So minus comes out, N comes out, F comes out. It becomes D of E cell divided by dt, right? And this particular term is valid at constant pressure. You have kept pressure constant in the beginning, right? And this particular term is equal to minus times delta S for the reaction. So minus gets cancelled out. So the first result which we got, which you are going to remember from now on, whenever they ask you calculate the entropy change in the galvanic cell, right? You'll be writing this expression NF dE upon dt at constant. My dear students, this particular result you will be using to calculate what? To calculate entropy change in case of the galvanic cell. N, number of moles of electrons exchanged. F, Faraday's constant, 96500. This d by dt, this is something which you call as temperature coefficient of the cell. Temperature coefficient of the cell, which can be positive as well as negative. If you ask me the units of temperature coefficient, d by dt, this is change in EMF, change in temperature. EMF is volt, temperature is Kelvin. So its SI unit is going to be volt per Kelvin. This temperature coefficient. Perfect. So this is how you are going to calculate delta S for the cell reactions. Similarly, if they ask you to calculate delta G for the reaction, delta G is simple, minus NF E cell, right? So two parameters are done. If they by chance ask you about delta H for the reaction, you know your delta G, as per thermodynamics, delta G is equal to delta H minus T delta S, right? Now, when it comes to the cell reactions, you'll write RR everywhere. Perfect. Now, delta G value you know, delta S value you know. From here, you can calculate delta H. Let's get to know what will be the value of delta H. Let's try to understand. See, guys, we know delta G is equal to delta H minus T delta S, right? So from here, you can say delta H will be equal to delta G plus T. This is delta S, right? So I would say delta H for the reaction is equal. Delta G is minus NF E cell, right? Plus T. Delta S is NF dE upon dt. NF dE upon dt at constant pressure. So let's make a finalized result. So delta H for the reaction is equal. If I take NF common, it's going to be what? It's going to be minus E cell plus it's going to be dE upon dt, which is what you call as temperature coefficient of the cell at constant pressure multiplied by T. So this is the general result which you can remember also to calculate delta H for the galvanic cell. So they'll be asking few questions. First, they can ask delta G for the cell, for the galvanic cell, or they can ask delta S for the galvanic cell, or they can ask delta H for the galvanic cell. And these are the equations which you can use to calculate delta G, delta S, or delta H. Or sometimes they might ask you about the efficiency of the galvanic cell. Sometimes they can ask you about the efficiency of the galvanic cell as well. And how do you calculate the efficiency of the galvanic cell? It is simple. Mod of delta G of the cell divided by mod of delta H for the cell multiplied by 100. This is the general expression which you can use to calculate the efficiency of the galvanic cell. Perfect. Provided you know delta G value, you know delta H value, just divide them, multiply with 100, get the efficiency of the galvanic cell as well. Okay. Perfect. Okay, guys. Now here there can be a question asked too. I'm writing the topic as variation of EMF with temperature. How EMF varies with temperature. This can be asked too. How EMF varies with temperature, right? My dear students, I'm going to divide this topic into two categories here. I'll be dividing this topic into two categories. It's simple, it's very simple. Those galvanic cells whose temperature coefficient is positive. This is my first category of galvanic cells. And those galvanic cells whose temperature coefficient is negative, right? So I've got two types of galvanic cells. First, those galvanic cells with temperature coefficient positive and those galvanic cells with temperature coefficient negative. Let's see how their EMF varies with temperature. Does EMF increase on increasing the temperature or does it decrease? Let's get to know. See. So first of all, I'm talking about that particular galvanic cell whose temperature coefficient is positive. Right? Now, my dear students, for example, in this particular cell whose temperature coefficient is positive, if you increase the temperature of the cell, upon increasing the temperature, what will happen to dT value? Change in temperature. Change in temperature is final minus initial. Final temperature minus initial temperature. This term will be positive. Simple. When you increase the temperature, dT will be positive. Change in temperature is positive. Now this overall term is positive. And already we know, since we increase the temperature, upon increasing the temperature, dT value is positive. So dT value is positive. Denominator is positive. If denominator is positive and the whole term is also positive, for the whole term to be positive, I'll say dE value should be positive as well. It should be positive as well. dE positive means when dE will be positive, when change in EMF will be positive, if the final EMF will be greater than initial EMF. So what exactly you concluded from here? You saw upon increasing the temperature, EMF, is it increasing or decreasing? E2 is greater than E1. I'll say upon increasing the temperature, the EMF, it increases, right? The EMF, it increases. So directly you can say E cell is directly proportional to temperature for those cells which have got temperature coefficient positive, right? Which have got positive temperature coefficient. I hope this is clear. Similarly, those galvanic cells which have got temperature coefficient negative, how their EMF varies with temperature. See, for example, if you increase the temperature here, upon increasing the temperature, dT value will be positive. Absolutely, dT is positive. So denominator, dT, it is coming out to be positive. Denominator is positive. But whole term, overall term has to be negative. Since denominator is positive and overall term has to be negative, for the overall term to be negative, I'll say this dE value has to be negative. This dE value, it has to be negative, then only the overall value will be negative. Now tell me one thing. When this dE will be negative, dE is change in EMF. It is only negative if E2 will be less than E1. Right? Change in EMF will be only negative if final EMF will be less than initial EMF. So upon increasing the temperature, what is happening to EMF? EMF is decreasing. I'll say E cell here will be inversely proportional to temperature. But it is valid for those cells which have got temperature coefficient as negative. Is this clear? Is this clear to everyone? Let me know quickly in the chats if this is super clear to everyone. Right? Quickly. So what you exactly, these are the two things which you have to remember at the end, nothing else. E cell is directly proportional to temperature for those cells which have got temperature coefficient positive. E cell is inversely proportional to temperature for those cells which have got temperature coefficient negative. That's it. Okay. Okay, guys. Is every single thing clear till here? Because everything is dealt with detail. Everything is done with detail. Okay. And here you have to remember how many results. Delta S result you have to remember. Delta G result you have to remember. And delta H result you have to remember. If you do not want to remember the delta H, it's okay also. Because once you get delta G value, once you get delta S value, you can easily calculate delta H from this particular equation. One and the same thing. Okay. Perfect, guys. Do you want to solve one question on this particular topic? Do you want to solve one question on this particular topic? Let me know once quickly. Do you want to do that? Okay, let's have a look on the question which can be asked from here. I'm writing the question, okay? Just a second. One simple question I'm giving you. The question is like this. The EMF of the cell, it is given to us as 1.018 volt. EMF of the cell is given to us as 1.018 volt. Temperature coefficient of the cell, dE upon dt at constant pressure. This temperature coefficient of the cell is given to me as -5 multiplied by 10 raised power -5 volt per Kelvin. Okay. What are we supposed to calculate? Calculate delta G, delta H, and delta S. And delta S for the reaction. And the reaction is like this. Cadmium dye positive plus 2 electrons, it gives cadmium solid, right? And temperature, this reaction is carried out at temperature 25 degrees centigrade. This is one of the questions which can be asked from this topic. Look at the question carefully. The reaction is given. So first of all, how many moles of electrons exchanged? 2. So N value is 2 first of all. N value is 2. This is something which you got. Now, delta G. Delta G. Delta G is nothing, that's minus N of E cell. Right? So minus N value is 2. Faraday's constant, 96500 coulombs. Right? E cell value is also given. 1.018 volts. So every value is taken as per SI system. That means delta G value will be also coming as per SI system. As per SI system, the value of delta G is joules. So the final answer will be in joules. Number 1. Number 2. Delta S is simply going to be equal to NF dE upon dt. NF dE upon dt at constant pressure. So what is N value? N value is 2. Faraday's constant is 500 coulombs. dE by dt. What is dE by dt? Temperature coefficient. That is -5 into 10 raised power -5. So by solving this particular equation, you'll be getting the value of delta S. And delta S units you already know. Delta S is basically Q by T, right? Entropy change, Q by T. So it has to be joules per Kelvin. Now delta H. Delta H, you have to calculate. How you'll be calculating delta H? Either you'll be using the direct result, which I gave you, or you can use this equation directly. Delta G is equal to delta H minus T delta S. Now, my dear students, delta G already you calculated. Delta S you calculated. Temperature is given. Converted in Kelvin. So from here you can calculate delta H. Nothing else. Right? Delta H value will be also in joules. Right? These sort of questions can come. These sort of questions can come. And there has been, I mean, in your NEET examination, question has never been asked from thermodynamics of the cell. So this time they might ask it from here. So I believe we have completed the EMF part. EMF part of electrochemistry is completed. Now it is time to enter into one more part of the chapter, that is electrolytic part. And that electrolytic part we shall be starting on Thursday, day after tomorrow. So Thursday, Thursday at 6 p.m. we'll have one more session in which we shall be completing the electrolytic part of this particular chapter as well. Okay? Perfect, people. I think this much is enough for today. Yeah? Or do you want to study more? This much part is enough for today, okay? And do let me know in the comment section if you actually got all the points related to this particular session. Okay, let's catch up day after tomorrow. Till then, you guys take care. God bless you all. Let's kickstart the preparation again. Yeah? Bye bye, guys. Take care.